Imagine a pitch-black void where the rules of human perception completely shatter. Tonight, we plunge into an idea that sounds incredibly basic at first glance, but actually stands as one of the most mind-bending pillars of modern cosmic science. It is the concept of a light year. You have almost certainly encountered this exact phrase 1,000 times before. Space experts and authors throw it around constantly whenever they describe the stars. However, there is a profound truth that almost everyone completely misses. When you truly grasp what a light year actually means, when you deeply process the sheer physical scale of the distance it defines, it fundamentally transforms your entire perspective on our universe. It is not just an impossibly large number scrawled on a white board. It represents a span of space so colossally grand that it actively challenges the limits of human consciousness to even map it out. And by the time we finish this exploration, you will understand with absolute clarity exactly why space scientists desperately require this specific unit of measurement, and why no standard Earth-based metric could ever serve the same purpose. Before we dive any deeper into this cosmic journey, if you find this type of deep investigation fascinating, a quick tap on the like button or subscribing to the channel helps immensely in spreading this knowledge. It is a tiny, effortless motion for you, but it yields a massive, wonderful impact for me as a creator. Now let us immerse ourselves fully. Let us begin our investigation with an idea that feels completely familiar to everyone: the concept of distance. You possess an intuitive, instinctual grasp of distance within the boundaries of your normal daily routine. You are fully aware of how much effort it takes to travel to your local grocery store, to commute to your place of work, or to drive to a neighbouring town. These are specific spaces you can easily visualise inside your head because you have personally navigated them multiple times. You maintain a perfectly clear perception of what they signify regarding the passage of minutes, the physical energy required, and the exact sights you will encounter along your path. A single kilometre represents roughly the spatial distance you can cover on foot in about 10 to 12 minutes when maintaining a standard, relaxed walking pace. These traditional systems of measurement function flawlessly for the practical demands of our ordinary human routines. If a close acquaintance tells you that the local market is situated exactly 5 kilometres away, you possess an immediate understanding of how much time will be required to pilot your vehicle to that location. You can easily map out the entire trajectory inside your mind. Perhaps your journey will take you past a couple of familiar traffic lights. Perhaps you will observe a few recognisable storefronts along the route. The spatial interval is entirely tangible and easy to interpret. If someone mentions that a specific city is located 200 kilometres away, you can organise your travel schedule with absolute confidence. That equates to roughly 2 hours of active highway driving. You will make sure to top off your vehicle's fuel reservoir, and maybe you will decide to pack a few items to snack on. You might even schedule a brief pause to stretch your legs at the midpoint of the drive. These specific metrics are structured around a human scale of existence. They align neatly with our personal encounters and our direct physical perceptions. As a species, we evolved specifically to interpret distances that we could comfortably cross by walking within a single sunrise, spaces that our eyes could clearly scan, and dimensions that directly affected our immediate survival and basic land navigation. However, these familiar units of measurement begin to turn incredibly clumsy and awkward the moment we pivot to discussing truly immense scales of separation. The total geographic span separating New York City from Los Angeles amounts to roughly 4,500 kilometres. That particular value remains completely manageable as a statistical figure. It translates to approximately a 5-hour commercial airline flight. Everyday citizens undertake that exact transcontinental journey all the time. They traverse the entire breadth of the nation. They witness the shifting geometry of the Earth below, watching it transform from the dense urban centres of the Atlantic coast to the sweeping, flat agricultural plains of the Midwest, shifting into the jagged peaks of the Rocky Mountains, moving through the arid terrains of the Southwest deserts, and terminating at last at the edge of the Pacific coastline. The entire excursion is undoubtedly extensive, but it remains fully within the boundaries of what is achievable. It stays entirely within the perimeter of human capability. You can easily conceptualize yourself undertaking that specific voyage. Furthermore, the total structural circumference of planet Earth, measured directly at the equator, equals roughly 40,075 kilometers. That stands as an undeniably large numerical figure, yet it still constitutes a physical value that we can mentally process from a conceptual standpoint. Historic nautical navigators successfully managed to sail around the entirety of the globe, which proves to us that it is entirely feasible to navigate that massive distance, even if the endeavour demands long consecutive months of perilous travel. The pioneering global expedition, captained by Ferdinand Magellan, required a full 3 years to completely circle the planet, lasting from the year 1519 until the year 1522. In our contemporary world, high-speed commercial passenger aircraft could theoretically circle the entire planet in roughly 45 hours, provided you could coordinate a series of continuous connecting flights that travelled all the way around the globe. The planet Earth is certainly massive when viewed from our personal vantage point as we stand directly upon its crust, but it is not so astronomically massive that it completely defies our capacity to understand it. It remains a bounded, finite object that you could, in a purely theoretical sense, map out and examine entirely. But now, let us push our boundaries out much wider. The physical separation stretching between the Earth and our Moon measures roughly 384,000 kilometres. This specific threshold is precisely where our standard systems of measurement begin to feel completely inadequate and broken. 384,000 kilometres. That is a value that is extraordinarily difficult to map out in any truly practical or meaningful fashion. It does not resemble the act of driving your car across the territory of a nation. It does not mirror the experience of navigating a ship around the circumference of the globe. It represents something altogether alien to our regular lives. There is no paved highway to track, no physical landmarks to cruise past, and no roadside stations to rest at along the trajectory. It is nothing but pure, unadulterated distance. Absolute distance expanding across an entire gulf of completely vacant vacuum. How could a human being even begin to organise a voyage across a span that immense? The courageous Apollo space travellers required approximately 3 full days of continuous travel to cross the void from the Earth to the Moon. They achieved this by riding inside hyper-engineered vehicles driven by incredibly volatile rockets that propelled them to velocities hovering around 11 kilometres every single second. That translates directly to an astonishing speed of roughly 39,600 kilometres per hour, which is approximately 400 times faster than the speed you maintain while driving along a standard highway. Contemplate that specific metric for just a brief moment. 400 times swifter than the highest velocity you have ever personally experienced behind the wheel of an automobile. And even when proceeding at that breathtaking rate of motion, an enterprise which demanded the creation of some of the most colossally powerful propulsion systems ever designed by the human species, systems that incinerated truly mind-boggling reserves of chemical propellants, it still required 3 entire days of travel time, 3 full days of hurtling through a completely desolate void at velocities that no human body had ever encountered in all of history, simply to arrive at our absolute closest neighbour in the night sky. And we must remember that this immense journey only brings us to the Moon, which is the most immediate celestial object orbiting the Earth. The Moon is positioned so incredibly close to us that you can readily observe it with nothing more than your naked eyes. You can easily identify discrete geological features across its cratered terrain, using nothing more than a basic pair of handheld binoculars. It is suspended right there, looming visibly within our upper atmosphere. Yet, despite that constant visibility, it still demands 3 continuous days of high-velocity rocket transit to bridge the gap. When we expand our scope to evaluate the sheer physical spacing separating us from the other planets in our system, or the distance to our parent star, or the spans separating us from alternative suns, kilometers transform into a completely useless metric. The mathematical values amplify to such a monumental degree that they lose all trace of practical significance. They stop functioning as distances you can relate to in any genuine manner, and instead degrade into abstract mathematical characters printed across a sheet of paper. The total spatial separation stretching between the Earth and our Sun is roughly 150 million kilometres. Attempt to truly map that metric out inside your mind. You find that you cannot do it effectively, can you? Your neurological architecture merely perceives that value as a colossally large digit, but you do not possess any sort of native, instinctual appreciation of what that space truly represents. There is absolutely no event or encounter within your standard daily existence that can properly prime your consciousness to comprehend a spatial interval of that magnitude. Absolutely nothing throughout the long timeline of human evolutionary adaptation equipped our minds to actively process distances on the scale of 150 million kilometres. We evolved specifically to comprehend the spatial gap separating us from the nearest freshwater spring, the total distance required to trek to our tribal hunting grounds, or the literal footprint we could cover on foot before the sun sets. We were never engineered to decipher the reality of 150 million kilometres. The specialised Apollo lunar spacecraft that ferried human crews to the Moon cruised at an average velocity of roughly 11 kilometres per second. If you were to maintain that exact velocity on a trajectory toward our Sun, it would demand roughly 160 days of non-stop travel, which amounts to over 5 full months, just to bridge that distance. The most extraordinarily swift automated probe ever designed and launched by human hands, known as the Parker Solar Probe, achieves blistering top velocities, reaching up to 192 kilometers per second when it makes its closest approaches to the Sun. It accomplishes this by utilizing the immense gravitational field of neighboring planets to slingshot itself forward, accelerating to higher and higher rates of speed. Yet even when moving at this absolutely staggering velocity, a pace that is roughly 17 times swifter than the velocity managed by the historic Apollo lunar spacecraft, this advanced probe still requires consecutive months of time to trace its loops around the Sun. And we must keep in mind that this specific star is exceptionally close to us. It is situated right here in our immediate cosmic backyard. It is the exact star around which our own world orbits. It serves as the primary origin point for all the radiant illumination and thermal energy that permits organic life to thrive on Earth in the first place. We look up and see it look down upon us every single day. It is a deeply ingrained, familiar presence, and yet it remains positioned a staggering 150 million kilometres away from us. It is a spatial expanse so colossally vast that even our most hyper-accelerated modern robotic space vessels require long months just to cross through it. The moment we transition to analysing the distances that separate our system from alternative stars, even the immense space between the Earth and our Sun shrinks until it appears completely microscopic by comparison. The Sun represents our absolute nearest stellar neighbour, and it is located 150 million kilometres away. The very next closest star system beyond our own, which is named Proxima Centauri, is situated roughly 266,000 times farther away than that already massive distance, 266,000 times more distant than a spatial span that already requires our most advanced high-speed robotic probes consecutive months to navigate. This staggering reality is precisely why space scientists and astronomers desperately required an entirely different unit of measurement. They did not implement this shift because they enjoy inventing convoluted ideas, nor because they harbour a desire to perplex the general public with bafflingly large mathematical figures. They did it simply because standard kilometres cease to function in a meaningful capacity when your task is to measure the architecture of the cosmos. Attempting to utilise standard kilometres to quantify the spatial separation between individual stars would be conceptually identical to utilising tiny millimetres to map out the geographic distances separating sovereign nations across the globe. While it remains technically achievable in a purely mathematical sense, it is completely absurd and useless from a practical standpoint. The resulting numerical expressions expand to such a degree that they lose all cognitive anchors to reality. They cease to register as actual physical spans and instead devolve into pure numbers. They become nothing but detached mathematical principles that completely fail to connect with any baseline human experience. Consequently, the global community of astronomers formulated a completely separate metric, the light year. However, there is a fundamental rule that you must absolutely cement in your mind right from the very beginning of this discussion. A light year does not constitute a measurement of temporal duration. I am fully aware that it explicitly contains the word year directly inside its title, which naturally misleads the human brain into classifying it as a statement of time, but it is absolutely not that. A light year is strictly a unit of physical distance. It is defined precisely as the total spatial separation that a beam of light traverses across the vacuum of space over the course of one full calendar year. Now we must ask ourselves, why would scientists anchor an entire universal system of measurement upon the movement of light? They did so because light occupies an incredibly unique status in our universe. Light represents the absolute swiftest phenomenon in the entire fabric of existence. Absolutely nothing in the cosmos can travel at a speed that exceeds the velocity of light. This rule does not merely represent a temporary technological benchmark or a speed limit that we simply haven't figured out how to shatter yet with superior engineering. It is an unyielding foundational law of universal physics. The speed at which light propagates is a perfectly constant, unshifting value that remains identical regardless of where you are located in the cosmos. Whether you are standing directly on the surface of the Earth, exploring the desert plains of Mars, navigating through an entirely separate galaxy, or drifting at the absolute boundary of the observable cosmos, light always travels at the exact same velocity. Light races through the void at a speed of approximately 300,000 kilometers every single second. Let me state that metric once more because it is absolutely vital to our understanding. 300,000 kilometers per second. With every single tick of a clock, a beam of light covers a distance of 300,000 kilometers. This value does not represent a loose approximation, a rough guess, or a casual estimate. It has been calculated by modern researchers with a degree of extraordinary mathematical precision. The absolute exact numerical value is defined as 299,792.458 kilometers per second. However, for the general concepts we are analysing tonight, rounding it to 300,000 kilometres every second is perfectly close enough to the truth. That is an incredibly mind-boggling rate of motion. To help place this velocity into a relatable framework, a single beam of light can circle the entire equatorial circumference of the planet Earth roughly 7.5 times within one solitary second. In the brief flash of time it takes for you to snap your fingers together, light could circle our entire planet multiple times over. Within the span of one single second, light possesses the ability to race from New York City all the way to Los Angeles and back again, roughly 37 times consecutively. It is a rate of speed that is nearly impossible for the human mind to visually construct, because absolutely nothing we interact with inside our normal earthbound existence travels anywhere near that blistering velocity. The swiftest mode of transportation that most everyday citizens ever personally experience is a standard commercial airplane. A modern jet airliner cruises through the sky at a velocity of roughly 900 kilometers per hour, which breaks down to approximately 0.25 kilometers per second. A beam of light travels more than 1 million times faster than that commercial jet aircraft. The absolute fastest land vehicle ever constructed in human history, a specialised record-breaking car known as the Thrust SSC, managed to achieve a top speed of roughly 1,200 kilometers per hour, which translates to about 0.33 kilometers per second. Light moves approximately 900,000 times swifter than that hyper-engineered land vehicle. Even if we evaluate the single fastest space vessel humans have ever managed to build, the Parker Solar Probe cruising at its absolute maximum velocity of 192 kilometers per second, it still only manages to reach about 0.064% of the true speed of light. It is moving at a rate that seems blindingly fast by any traditional human metric, but when placed side by side with the velocity of light, it is practically crawling along. When you enter a dark room and flip a standard wall switch, the illumination appears to strike your eyes completely instantaneously because the physical dimensions of the room are so incredibly compact. The light only needs to travel from the glowing bulb to your retina, a journey that consumes roughly 10 billionths of a single second. That duration is so incomprehensibly brief that there is absolutely no delay that a human being could ever perceive. As far as your brain's processing centres are concerned, the illumination manifests instantly. However, the reality is that the light did have to travel physical space. It consumed a finite amount of time to make that trip. It is simply that the temporal window was so microscopically short that it is fundamentally impossible for you to detect it. By contrast, when you look up into the sky and observe the sun, you are not viewing it as it exists in this exact present moment. You are actually observing the sun as it existed 8 minutes and 20 seconds in the past, because that is the precise length of time required for photons of light to travel all the way from the sun to the surface of the Earth. Our parent star is positioned at such a profound distance from us that even light itself, screaming through the void at 300,000 kilometers every single second, still requires over 8 full minutes to cross the gap. This reality introduces a deeply fascinating scientific truth. If a catastrophic event occurred on the surface of the sun right this second, if it suddenly shifted its colour, went completely dark, or suffered a massive explosion, no human being on Earth would have any idea for over 8 minutes. The event itself would have already taken place, but the actual light waves carrying the physical information regarding that event would still be actively travelling across space toward us. We would continue to observe the sun looking completely normal, seeing it as it used to be rather than how it currently is, for over 8 minutes. Similarly, when you look up at the moon at night, you are viewing it as it was roughly 1.3 seconds ago, While that does not represent a massive temporal delay, it remains a real delay nonetheless. When the historic Apollo astronauts were exploring the lunar surface and conversing with mission control operators back on Earth, every single word they spoke required 1.3 seconds to navigate the void to Earth. Furthermore, every response transmitted back by mission control required an additional 1.3 seconds to cross the gap back to the Moon. This natural physical limitation generated a mandatory pause of nearly 3 full seconds inside every single back and forth communication exchange. You can easily hear this distinct pause when you listen to the original audio archive recordings today. There is always this lingering gap, this specific transmission lag, because the radio frequencies carrying the sound of their voices could only move at the speed of light. And even light demands a finite amount of time to cross the physical gap separating the Earth from the Moon. Light does not move across the universe instantaneously. It possesses a distinct, measurable velocity. And that velocity, while unimaginably swift, is still entirely finite. This realization stands as one of the most monumental milestones in the entire history of physics. Prior to the closing decades of the 1600s, the vast majority of human thinkers simply took it for granted that light moved instantaneously. You opened your eyelids and you immediately perceived your surroundings. Because of this everyday experience, it seemed completely logical that light must be an instantaneous phenomenon. However, in the year 1676, a brilliant Danish astronomer named Ole Rømer was conducting highly meticulous observations of the moons of Jupiter when he stumbled upon something deeply anomalous. He noticed that the exact times when these moons were eclipsed as they slipped behind the massive body of Jupiter shifted systematically, depending on where the planet Earth happened to be positioned along its orbital path around the Sun. Whenever the Earth was positioned closer to Jupiter along its orbit, the observed celestial eclipses took place noticeably earlier than standard mathematical models predicted. Conversely, whenever the Earth was positioned at its farthest point from Jupiter, the eclipses occurred noticeably later than expected. Rømer experienced a flash of insight and realized that this variation occurred because the light waves required a finite amount of time to travel the differing physical distances separating the planets. He computed that light required roughly 22 minutes to traverse the entire diameter of the Earth's orbital path. His final calculated speed wasn't perfectly accurate, because the scientific community of his era did not yet possess the exact physical dimensions of Earth's orbit. Nevertheless, he conclusively demonstrated to the world that light operates at a finite velocity. In our modern era, we understand the speed of light with an unparalleled degree of precision. We have verified its value using advanced lasers, ultra-precise atomic clocks, and highly sophisticated laboratory gear. We have validated that it is an immutable constant, one that never alters regardless of how fast you are moving or where you are located in space. And we have uncovered the fact that this specific velocity, this cosmic constant, is woven directly into the very structural fabric of space and time itself. It is far more than just an arbitrary speed that light happens to maintain as it travels. It is a foundational characteristic of space-time itself. Therefore, a light year represents the precise physical distance that light covers over the course of 1 full year while moving at this constant velocity. Let us calculate that value mathematically. Light propagates at a speed of 300,000 kilometers per second. There are 60 seconds contained within a minute, 60 minutes contained within an hour, 24 hours contained within a day, and 365 days contained within a standard year. If we multiply all of these independent values together sequentially, 300,000 times 60 times 60 times 24 times 365, we arrive at an approximate total of 9.46 trillion kilometres. To state the value with absolute mathematical accuracy, it is 9,460,730,472,580.8 kilometres. However, to keep our expressions clean and simple, we generally just state it as 9.46 trillion kilometres. That is the physical reality of a single light year, 9.46 trillion kilometres. It is not a duration of time, but a tangible span of distance. The total footprint that light, the swiftest entity in the entire universe, covers in a single year. And that is the exact numerical value that we are going to attempt to truly comprehend this evening. Because developing an authentic appreciation of what a light year signifies is completely mandatory if you wish to understand our true position within the cosmos, the staggering gaps that separate the stars, and the authentic scale of the universe. But before we can do that, we must have a serious conversation about what the word trillion actually means. Because the truth is that most human beings possess absolutely no real, intuitive understanding of how colossally huge this number truly is. We casually throw around terms like million, billion, and trillion in our standard everyday speech. We listen to news broadcasts detailing federal government budgets measured in the trillions. We read stories about hyper-wealthy billionaires, and we talk about millions of citizens. But we fail to grasp the gargantuan architectural chasms that separate these specific numbers from one another. They all simply register to our ears as vague, incredibly large numbers, so our brains mistakenly treat them as if they are roughly in the same ballpark, but they are not. The mathematical differences between them are thoroughly staggering. A single million is defined as 1,000 thousands. If you made a commitment to save $1 every single day, commencing this morning and proceeding forward without ever pausing, it would require roughly 2,740 years of continuous saving for you to accumulate $1 million. That is an incredibly long span of time, yet it remains fundamentally graspable to human thought. You can mentally map out a historical timeline that stretches back 2,740 years into the past. That historical window carries you all the way back to the era of ancient Greece, to the foundational years of the early Roman Republic, a specific epoch when human beings were already actively constructing large cities, authoring books, and forging complex civilizations. It is a timeline that fits within our historical comprehension. By contrast, a single billion is defined as 1,000 millions. Now, we are elevating our numerical scale by a massive multiplier of 1,000. If you were to save $1 every single second, not every day, but every single tick of the clock, you would need to wait roughly 32 years to successfully accumulate $1 billion. That represents more time than it takes for a newborn child to grow into complete adulthood. If you commenced counting integers aloud the second you emerge from the womb and maintain that count continuously without ever sleeping, without ever consuming food, and without ever taking a single breath or break of any kind, you would be 32 years old by the time you finally uttered the number 1 billion. Consider that reality. 1 million seconds equates to roughly 11.5 days. That is completely manageable. You can easily conceptualize a window of 11.5 days. It is less than a standard 2-week vacation, but 1 billion seconds translates to 32 years of your life. The sheer escalation from 1 million to 1 billion is completely monumental. Now let us examine a trillion. A trillion is defined as 1,000 billions, and this is the precise threshold where numerical values completely sever all remaining connections to anything we can relate to from our lived experiences. If you attempted to count sequentially to 1 trillion, operating a steady pace of 1 integer per second without ever stopping for a single moment, the task would consume roughly 31,700 years of time. Allow me to put that duration into a true historical framework. That span of time is vastly longer than the entirety of recorded human history combined. The development of agriculture, which served as the absolute baseline foundation for the rise of human civilization, was only achieved roughly 10,000 years ago. Prior to that monumental shift, every human being on the planet lived exclusively as nomadic hunter-gatherers, perpetually migrating from region to region, trailing wild animal herds and tracking seasonal vegetation patterns. The very first formal writing systems did not emerge until roughly 5,000 years ago in ancient Mesopotamia. The historic pyramids of Egypt were constructed approximately 4,600 years in the past. The invention of the wheel likely occurred roughly 5,500 years ago. To successfully count to 1 trillion, you would need to have initiated your count long before any of those historical milestones ever transpired. You would have needed to start speaking your numbers when human beings still existed, solely in tiny wandering tribal units. An era when there were absolutely no cities, no organised nations, no written records, no cultivated farms, and no permanent houses. You would have been forced to count continuously through the entire life cycle of human civilization, through every single invention ever devised, every scientific breakthrough, every empire that ever ascended to power and crumbled into dust, through every war ever waged, every peace treaty ever signed, and every single triumph and tragedy across the entire human experience. And after all of that, you would still be actively counting today, and you would still face thousands of remaining years before you finally arrived at 1 trillion. Let me try to make this number even more tangible. 31,700 years ago, early Homo sapiens were living through the depths of the last great ice age. Our ancestors were utilising basic chipped stone tools. They were actively hunting massive woolly mammoths and giant ground sloths. Humanity had barely begun its initial migration across the surface of the globe. Modern humans had only recently migrated out of the African continent and were just beginning to establish a presence across the regions of Europe and Asia. There was no structured language as we understand it today. There was no form of art in existence beyond the most basic, primitive cave sketches, and no form of technology available beyond sharp rocks and carved wooden spears. That is how deep into the ancient past 1 trillion seconds will carry you. And we must remember that a single light year consists of 9.46 trillion kilometres. Every single one of those kilometres is an actual physical kilometre. It is not a hypothetical or abstract unit of space. It is a real distance. The exact spatial interval you can cover on foot in about 10 to 12 minutes at a casual stride. And there are 9.46 trillion of those independent individual kilometres packed tightly into one single light year. 9.46 trillion separate distinct kilometre-long blocks of space, each one matching the length of a brief stroll to your neighbourhood market. Therefore, when we articulate the phrase that a light year spans 9.46 trillion kilometres, we are describing an interval of space that completely dwarfs absolutely anything within our daily experience. You can easily write the digits down on a piece of paper. You can perform calculations with it. You can plug it into complex scientific equations. But processing it in an intuitive, organic way is virtually impossible for the human mind. Our brains simply never evolved the cognitive capacity to interpret numbers of this scale. We evolved to keep track of the specific number of individuals living inside our immediate tribe, the count of animals roaming in a local herd, or the total number of days remaining before the weather shifts with the seasons. We can easily manage a count of a few hundred, or perhaps a few thousand if we apply intense concentration. But 9.46 trillion represents a value so profoundly detached from our cognitive architecture that it might as well be completely infinite. The absolute most effective method for understanding a light year is to construct our comprehension gradually, initiating our journey with spatial scales that we can easily grasp and then expanding outward step by step. We are going to navigate this conceptual path deliberately, progressing from the familiar terrains of our world to the unfamiliar realms of deep space, observing carefully as distances that initially appear monumental are reduced to total insignificance when compared to the stage that follows. Let us initiate this scaling process with 1 light second, which equates to 300,000 kilometers. That represents roughly the total distance from the Earth to the Moon, combined with 3/4 of the journey back again. Contemplate the reality of that speed. A beam of light departs from the surface of the Earth, races all the way to the Moon, which sits 384,000 kilometers away, bounces off the lunar surface and covers 3/4 of the return trip back to Earth, and the entirety of that massive journey occurs within the span of 1 single second, one solitary tick of a clock. When the Apollo astronauts were stationed on the lunar surface and talking with mission control operators back in Houston, there was a mandatory transmission delay of approximately 1.3 seconds in each direction. An astronaut would utter a phrase, and the team at mission control would not hear the audio for 1.3 seconds because the radio signal, travelling at the speed of light, required that precise duration to complete the cross-spatial trek. When the flight controllers spoke a reply, their audio required another 1.3 seconds to cross the void back to the Moon. Thus, every single conversation had a nearly 3-second gap permanently engineered into the exchange. It is a subtle phenomenon when you listen to the archived audio tapes today, but it is always present. There is always this distinct pause, this natural lag, entirely because of the physical space the signals were forced to traverse, and because absolutely nothing in physics, not even radio waves, can travel faster than the speed of light. Next, let us evaluate 1 light minute, which is defined as 60 light seconds, or roughly 108 million kilometers. The Sun is situated approximately 8 light minutes away from planet Earth, which translates to roughly 150 million kilometers. Therefore, a single light minute constitutes roughly 12% of the total spatial gap separating the Earth from the Sun. If you could somehow survive standing directly upon the Sun, which is obviously impossible because it is a colossal sphere of roiling plasma, featuring a surface temperature hovering around 5,500 degrees Celsius. But if you could theoretically stand there and look back toward the Earth, you would be observing our planet exactly as it existed 8 minutes and 20 seconds in the past. If planet Earth suddenly suffered a catastrophic explosion, you would remain completely unaware of the event for over 8 minutes. The disaster would have already occurred, but the actual light generated by that disaster, carrying the visual information across the vacuum, would require over 8 minutes to successfully cross the immense gap between the Earth and the Sun. This physical reality introduces major practical hurdles for modern deep space robotic exploration that most everyday citizens rarely consider. Whenever NASA engineers guide robotic rovers across the terrain of Mars, they are forced to contend with a permanent communication delay because Mars is located at an immense distance. At its absolute closest orbital alignment, when the Earth and Mars are positioned on the exact same side of the Sun, Mars sits roughly 56 million kilometers away from us, which equals about 3 light minutes. At its absolute farthest alignment, when the two planets are positioned on completely opposite sides of the Sun, the distance swells to roughly 400 million kilometers, which equals approximately 22 light minutes. This means that when the Perseverance rover is executing manoeuvres on the Martian surface, every single instruction transmitted from Earth requires anywhere from 3 to 22 minutes to actually land at the rover's receiver, depending on the current orbital positions of the planets. Furthermore, any diagnostic data or imagery the rover transmits back requires that exact same window of time to reach our receivers on Earth. It is completely impossible to pilot a rover on Mars in real time the way you would operate a standard remote-controlled toy car on Earth. The physical delay is simply far too long. Instead, NASA personnel must plan out the rover's navigational trajectories with immense care. They study images captured on preceding days, map out a safe path, author a complex sequence of automated commands, transmit that package to Mars, and then simply sit and wait. If an unexpected emergency transpires, if the rover accidentally wedges a tyre against a sharp rock or encounters an unmapped obstacle, the team on Earth cannot intervene immediately. They must wait for the diagnostic data to cross the void to Earth, a journey consuming between 3 and 22 minutes. Then they have to analyse the failure, formulate an engineering solution, write an entirely new sequence of commands, transmit those instructions back into space, and wait another 3 to 22 minutes for the commands to arrive at Mars. A basic issue that could be resolved in mere seconds with a remote-controlled car on Earth can easily consume an hour or more when operating across the distances of Mars. Moving up the scale, 1 light hour is defined as 60 light minutes. That equates to approximately 1,080,000,000 kilometres, over 1 billion kilometres. That is a spatial chasm so profoundly vast that even attempting to conceptualise it stretches human imagination to its breaking point. The planet Saturn, when it makes its closest orbital approach to planet Earth, is situated roughly 1.2 light hours away from us. Saturn represents one of the most distant planetary bodies that a human being can observe using nothing more than their naked eyes from the surface of the Earth. It is a stunning, ringed world that humanity has been studying since ancient times, and it sits roughly 1.2 light hours away. Throughout the timeline, when the Cassini robotic spacecraft was actively orbiting Saturn from the year 2004 until 2017, capturing breathtaking close-up imagery of the ringed planet and its diverse collection of moons, there was a permanent delay of over an hour between the exact instant the camera snapped a picture and the moment that image actually reached Earthbound computers. The spacecraft would record a photograph, compress it into digital telemetry data, and broadcast it through space as a radio signal screaming at the speed of light. And over an hour later, researchers waiting on Earth would finally receive the transmission. Because of this reality, the Cassini spacecraft could never be operated via real-time piloting. Engineers and scientists were completely unable to monitor what the vessel was seeing live and adjust its trajectory on the fly the way you might guide an automobile or pilot an aerial drone. Instead, they were forced to program highly elaborate sequences of operations days or even weeks in advance, upload the code to the spacecraft's memory banks, and maintain absolute faith that Cassini would execute the script flawlessly. If an anomaly flared up, the spacecraft had to possess enough onboard autonomy to diagnose the issue independently, recognize the threat, and automatically drop into a protective, safe mode. This was mandatory because by the time the notification of the error travelled all the way back to Earth and new troubleshooting commands could be authored and transmitted back, over 2 full hours would have ticked away. The physical environment and conditions surrounding the spacecraft could have altered completely within that temporal window. Let us scale up to 1 light day, which comprises 24 light hours, or roughly 25,900,000,000 kilometres. We have now entered spatial realms where even our most hyper-accelerated space vessels appear unbelievably slow by comparison. Voyager 1, the legendary robotic probe launched by humanity in the year 1977 and currently holding the record as the single most distant human-made object from planet Earth, is positioned roughly 24 light hours away as of the year 2025. It has been hurtling through the vacuum for nearly 50 consecutive years, moving at a velocity of approximately 17 kilometers per second, which converts to roughly 61,200 kilometers per hour. That is an extraordinarily blazing speed by any conceivable human standard. Moving at that rate, you could travel from the Atlantic coast of the United States to the Pacific coast in roughly 2 minutes flat. And yet, after nearly 5 full decades of uninterrupted movement through the absolute vacuum of space, with completely zero atmospheric friction to slow its progress, Voyager 1 still has not covered one single full light day of distance from Earth. This specific boundary corresponds roughly to the location of the heliopause, which is the physical frontier where the dominant influence of our Sun terminates and true interstellar space commences. The heliopause represents the exact cosmic boundary where the solar wind, the relentless outward rushing torrent of highly charged particles emitted by the Sun in every direction, finally loses its momentum and blends into the interstellar medium. The interstellar medium is the incredibly thin, sparse gas that populates the vast gaps separating individual stars. Voyager 1 successfully crossed through this historic boundary in the year 2012, marking a monumental milestone in human exploration by becoming the first piece of human engineering to exit the solar system and enter interstellar space. It was an unforgettable moment for our species. Yet, from a cosmic perspective, it remains positioned well within one light day of our Sun. In the grand geography of the universe, it is still located right here in our immediate neighbourhood. Moving further out, one light week spans 7 light days, which translates to roughly 181 billion kilometres. We are now contemplating a domain of space where absolutely nothing created by human hands has ever been, and where nothing we build will arrive for long decades or even centuries to come. This is the realm of true deep space, positioned far beyond the orbits of the known planets and far beyond anything we have ever directly investigated. Out in this desolate expanse, our Sun would completely cease to appear as the blinding, all-powerful engine of illumination and heat that we experience from Earth. It would instead shrink into just another bright star in the sky, noticeably more brilliant than the stars surrounding it, certainly, but ultimately just a singular point of light pinned against the dark void. If a human being could somehow be suspended out there, floating in the open vacuum of space, a full light week away from the Sun, you would look back and see our Sun as a brilliant stellar point. But you would also observe thousands of alternative stars strewn across the absolute blackness of the sky. You would realise, perhaps for the very first time in your life, that our Sun is merely one single star among a vast sea of many. Next, let us evaluate one light month, which constitutes roughly 30 light days, or approximately 778 billion kilometres. At this immense threshold of separation, if you were to point a powerful telescope back toward the Sun, you would see it merely as an ordinary star, matching the brightness of numerous other stellar bodies scattered across the night sky. The entire solar system, encompassing all of our massive planets, their diverse moons, the asteroid belts, and the sweeping paths of comets, would be rendered almost completely invisible. Even if you utilised a highly advanced telescope, you might barely manage to identify Jupiter as a microscopic, faint speck of light, but all of the inner rocky planets would be completely swallowed up by the overwhelming glare of the Sun, absolutely everything we conceptualize as the solar system, all of the diverse worlds we have spent centuries mapping, the planets where we have landed robotic probes, and the celestial bodies we know so well, would be compressed into a tiny, indistinguishable patch of space clustered around an unremarkable star. And finally we arrive at one full light year. One light year comprises 365 light days. It equals 12 light months. It spans 52 light weeks. It contains 8,760 light hours. It breaks down into 525,600 light minutes. And it consists of exactly 31,536,000 light seconds. Observe with care just how rapidly these numerical scales accelerate outward. We initiated our progression with one single light second, which already constituted a monumental distance within a human framework, covering the space from the Earth to the Moon, and most of the way back again. From there, we have been continuously multiplying that unit by larger and larger numerical values. 60 seconds inside a minute, 60 minutes inside an hour, 24 hours inside a day, 7 days inside a week, 30 days inside a month, and 12 months inside a year. And after all of that compounding scale, we have only just arrived at the baseline metric of one solitary light year, 9.46 trillion kilometers. That is the literal physical footprint that a beam of light covers over the course of 1 year, cruising at 300,000 kilometers every single second for 365 consecutive days without a moment of pause. And this is the foundational unit of measurement that space scientists must utilize to quantify the spatial intervals separating individual stars, because stars are isolated from one another by spaces so immense that they can only be cleanly calculated in light years. Absolutely nothing smaller makes a modicum of sense when your task is to map out these staggering cosmic dimensions. So we must ask, why do astronomers insist on using light years? They use them because every single alternative option is significantly worse. Imagine if space scientists attempted to utilize standard earthbound kilometers to express every single cosmic distance. The star Proxima Centauri is located roughly 40,140 billion kilometers away from us. That is an incredibly awkward number to speak aloud. It is exceptionally difficult to memorize, and it completely fails to provide your brain with any sort of intuitive appreciation of the actual spatial separation. However, if I communicate the data point that Proxima Centauri is situated 4.24 light years away, that is a clean, manageable value. You can easily compare that metric against alternative cosmic distances. If one star is situated 4 light years away and a secondary star is located 40 light years away, your brain instantly recognizes that the secondary star is precisely 10 times more distant than the first. Furthermore, utilizing light years establishes a highly practical mathematical bridge that unifies physical distance with the passage of time. When you look up at a star that is located 4 light years away, you're automatically viewing light waves that departed from that star 4 years ago. You're literally gazing directly into the past. This profound unification becomes completely indispensable when studying the history of the universe. The velocity of light is far more than just a blindingly fast speed. It stands as the absolute structural speed limit of the universe. Nothing in existence can surpass it. And this is not a temporary engineering hurdle that humanity might eventually bypass with superior technology or more advanced propulsion concepts. It is an unyielding fundamental law of physics woven directly into the geometric blueprint of space-time itself. The speed of light isn't merely an arbitrary velocity. It is a foundational cosmic constant that dictates the exact interplay connecting space, time, energy, and matter. Albert Einstein's historic theory of special relativity, unveiled to the world in the year 1905, demonstrated conclusively that as physical objects accelerate toward the speed of light, highly bizarre physical anomalies begin to manifest. These anomalies are not merely interesting theoretical concepts or science fiction ideas. They are verified physical realities, confirmed by a century of meticulous laboratory experimentation. Time literally begins to slow down for the accelerated object when evaluated by stationary observers. This physical reality is scientifically designated as time dilation, and it has been measured directly with absolute precision. Simultaneously, the object's effective mass, or more accurately, its physical inertia, begins to amplify dramatically. It becomes progressively harder and harder to accelerate it any further. The literal quantity of kinetic energy demanded to accelerate the object higher increases without any upper boundary as you creep closer to light speed. To actually transition an object with mass to the literal speed of light would demand an infinite reservoir of energy, which is a flat impossibility. The universe simply does not contain an infinite supply of energy. Consequently, absolutely nothing that possesses mass can ever reach the speed of light. Let me break down exactly why this phenomenon occurs. Within our standard, low-speed daily routines, if you are riding inside a passenger train travelling at a velocity of 50 km per hour, and you throw a baseball directly forward at a speed of 20 km per hour, relative to the train, an observer standing stationary on the ground would see the ball moving at 70 km per hour. The independent velocities simply add together neatly. This principle appears completely intuitive, and it functions flawlessly for the standard velocities we experience in everyday life. However, Einstein demonstrated that this simplistic addition of velocities completely breaks down when dealing with speeds that approach the velocity of light. If you are piloting a futuristic spacecraft that is cruising at exactly half the speed of light, and you activate a high-powered flashlight pointed directly out the forward view screen, you might naturally assume that the emitted light would travel at 1.5 times the speed of light from the perspective of an outside observer. But it does not. The emitted beam of light still travels at precisely the standard speed of light, 300,000 kilometers per second, both from your personal vantage point inside the cockpit of the spacecraft and from the vantage point of a stationary observer watching your ship zip past from the outside. This reality sounds completely impossible on its surface. How can the exact same beam of light be moving at the identical velocity for both independent observers when one of those observers is already hurtling forward at half the speed of light? The answer is that the metrics of space and time themselves actively distort and adjust to ensure that the speed of light remains perfectly constant for everyone. If you are moving at an exceptionally high velocity, time itself literally ticks slower for you from the perspective of a stationary observer. Furthermore, physical distances measured along the exact direction of your motion actually contract and shrink. These are not optical illusions, psychological tricks, or technological measurement errors. They are genuine, measurable, physical distortions of reality. Time and space are not fixed, absolute canvases. They are completely relative constructs that warp depending on your state of motion. The singular thing in the entire cosmos that remains absolute, matching perfectly for every observer regardless of how fast they are moving, is the speed of light. This has been confirmed experimentally thousands of times over. Subatomic particles trapped inside high-energy particle accelerators are regularly pushed to velocities hovering right at 99.9% of the speed of light. We can precisely measure the exact duration of their lifespans before they undergo natural radioactive decay. And what we discover is that particles moving at 99.9% of light speed survive significantly longer than identical particles that are sitting completely at rest in the lab. Time is literally passing at a slower rate for them. This is not a guess. it is a measured physical fact. Furthermore, the global positioning system satellites that orbit high above the Earth move at sufficiently high velocities and sit far enough outside the planet's primary gravitational well that time dilation becomes a highly measurable factor. The highly precise atomic clocks installed aboard GPS satellites tick along at a slightly altered rate compared to identical atomic clocks situated down on the ground. If the software running the GPS network did not actively apply mathematical corrections to account for this relativistic time dilation effect, your phone's navigation apps would drift out of alignment by several kilometers within the span of just a few hours. The very fact that your digital maps function correctly every day serves as undeniable physical proof that time dilation is a real phenomenon. Similarly, cosmic rays, extraordinarily high-energy particles streaming from deep space, generate unique subatomic particles known as muons when they collide with atoms in Earth's upper atmosphere. Muons are highly unstable particles that decay incredibly rapidly, possessing a natural half-life of a mere 2 microseconds. Operating at that rapid rate of decay, even when zipping downward at nearly the speed of light, these atmospheric muons should theoretically never be able to reach the surface of the Earth before completely decaying away. And yet, scientific sensors detect these muons hitting ground-level equipment all the time. Why does this occur? It occurs because, from our stationary perspective on the ground, the muons are zipping along so blindingly fast that time dilation physically stretches out their operational lifespans. What measures as a brief 2 microseconds from the personal perspective of the muon transforms into a much longer window of time from our earthbound perspective, long enough to permit them to easily bridge the atmospheric gap and strike the ground. The only entities in the entire universe that can travel at the absolute speed of light are particles that possess zero rest mass, such as photons, which are the fundamental particles of light. Photons possess absolutely no rest mass, meaning they do not require infinite energy to achieve light speed. In point of fact, photons are physically incapable of travelling at any other speed. They must always move at light speed. They cannot be slowed down, and they cannot be accelerated further. From the exact microsecond they are generated to the precise instant they are finally absorbed by matter, they move at exactly 300,000 kilometers per second, no faster and no slower. This is simply the immutable nature of what a photon is. This reality introduces immense, sobering boundaries for the future of human space travel that expand far beyond mere technological engineering hurdles. Even if our descendants eventually design flawless propulsion systems that grant them access to completely unlimited supplies of energy, and even if they successfully resolve every single engineering challenge imaginable, we still could never travel faster than the speed of light. The 4.24 light-years separating us from Proxima Centauri defines a mandatory absolute minimum travel time of 4.24 years of your life, even under a wildly optimistic scenario where we could instantly accelerate a starship to nearly the speed of light. And we must remember that this is merely the timeline required to reach our absolute closest neighbouring star. The vast majority of interesting destinations in the cosmos are positioned vastly farther away than that. Certain works of science fiction propose imaginative concepts to bypass this universal speed barrier. Ideas like warp drives that actively warp the geometry of space around a vessel, permitting it to effectively arrive at a destination faster than light, without ever physically moving faster than light through its local space. Concepts like wormholes, which create hypothetical shortcuts, cutting directly through the fabric of space-time to link completely separate regions of the universe, or notions like hyperspace, an alternate dimension of reality featuring completely different laws of physics, where faster-than-light transit is permitted. These are incredibly creative narrative devices, and certain concepts, like warp drives, do possess a loose foundation within the realms of theoretical physics. The famous Alcubierre warp drive model, proposed by physicist Miguel Alcubierre in the year 1994, represents a legitimate theoretical solution to Einstein's field equations that could permit faster-than-light travel by compressing space directly in front of a starship while expanding space directly behind it. However, the practical scientific hurdles are catastrophic. The Alcubierre model demands the utilization of exotic matter possessing negative energy density to function. No such matter has ever been discovered to exist anywhere in the real universe. Certain theoretical physicists believe that such matter might be fundamentally prohibited from existing by the laws of nature. Furthermore, even if exotic matter could exist, you would require a colossally immense quantity of it, potentially an amount of mass energy that exceeds the total content of the entire observable universe. There are also severe causality paradoxes to consider. If you possess the capacity to travel through space faster than light, you also mathematically possess the capacity to travel backward through time, which introduces severe causal paradoxes that could break reality. Wormholes, if they exist at all, would be extraordinarily unstable features that would violently collapse shut before a single subatomic particle could ever pass through them. Maintaining a wormhole open long enough to permit a starship to traverse it would demand energy inputs that might exceed the total energy present in the cosmos. And once more, you face severe causality issues, because wormholes can easily be converted into time machines travelling into the past, violating the laws of cause and effect. Hyperspace remains an entirely speculative concept with absolutely zero foundation within real physics or contemporary mathematics. It is a wonderful sci-fi storytelling mechanism that makes for excellent entertainment, but it holds completely zero connection to verified physics. There is absolutely no empirical evidence suggesting such a dimension exists or could ever exist. As far as humanity can state, based on over a century of highly rigorous, meticulous experimentation and celestial observation, the speed of light stands as an absolute, unyielding wall. It does not represent a challenge to be broken via superior engineering. It is a foundational law of the natural world. When we discuss stars that are situated hundreds or thousands of light years away, we are discussing spatial chasms that might be completely, fundamentally unreachable by any technology that obeys the laws of physics as we understand them. The light year doesn't merely quantify physical separation, it quantifies an absolute barrier, a universal limit, a boundary where our traditional rules of cause and effect are pushed to their absolute limits. To fully grasp the magnitude of a trillion, it is helpful to place this number against a historical backdrop. If we look back roughly 31,700 years, our primitive human ancestors were surviving in the harsh conditions of the last great ice age. During this era, humanity relied entirely on rudimentary tools crafted from stone. These early groups of people survived by hunting massive woolly mammoths and tracking giant ground sloths across vast landscapes. At this point in our evolutionary history, our species had only just begun to migrate outward from the African continent, slowly venturing into the unfamiliar territories of Europe and Asia. There was no sophisticated spoken language as we understand it in modern society, nor was there any advanced technology beyond basic wooden spears and fractured, sharpened stones used for cutting. The only real evidence of human expression from that distant epoch consists of the most primitive cave paintings left behind on stone walls. This incredibly long stretch of time, reaching all the way back to the dawn of primitive human existence, is exactly how far back you would have to go just to count 1 trillion seconds one by one. Now consider that a single light year is not just 1 trillion kilometres, but 9.46 trillion kilometres. Each individual kilometre within that massive total is a concrete physical distance. It represents a distance that a human being can walk in about 10 to 12 minutes if they maintain a steady, normal pace. Within 1 light year, there are 9.46 trillion of these distinct, individual, kilometre-long stretches. Every single one of them is the exact same length as a casual walk from your home to a local neighbourhood store. Therefore, when astronomers state that a light year spans 9.46 trillion kilometres, they are describing a physical reality that completely overwhelms and dwarfs any experience we encounter in our day-to-day lives. You can easily type this number out on a piece of paper, use it to complete complex scientific calculations, or plug it into mathematical equations. However, trying to truly understand and visualise this distance on an intuitive level is an almost impossible task for the human mind. The biology of our brains simply did not evolve to process and make sense of quantities that are this immense. Our evolutionary background prepared us to handle practical numbers, like tracking the total number of individuals living within our immediate tribe, estimating the size of a herd of wild animals, or keeping track of how many days remain before the seasonal weather changes. We are naturally equipped to count up to a few hundred, or perhaps a few thousand, if we dedicate our full focus and concentration to the task. But a number like 9.46 trillion is so incredibly far beyond our normal mental processing limits that it functions almost like infinity to our conscious minds. Because of this cognitive limitation, the most effective method to understand a light year is to construct our comprehension gradually, beginning with small distances that we can easily wrap our minds around, and then expanding that scale upward, step by step. We must take this intellectual journey at a slow, deliberate pace, transitioning carefully from the things that are familiar to the things that are entirely unfamiliar. By doing this, we can observe how distances that initially seem completely vast and overwhelming shrink down until they look tiny compared to the scale of the next step. Let us begin our upward scale with the concept of a single light second, which equals 300,000 kilometres. To put this into perspective, this is roughly equal to travelling from the surface of the Earth all the way to the Moon, and then completing 3/4 of the return trip back to Earth. Think deeply about what this means for a moment. When a beam of light leaves the Earth, it races across the void of space to reach our Moon, which sits 384,000 kilometres away. It bounces off the lunar surface and travels most of the way back to our planet, and this entire double journey takes place in the span of just 1 single second. During the historic Apollo missions, when the astronauts walking on the lunar surface communicated with the team at Mission Control in Houston, Texas, this physical reality created a very specific communication delay of about 1.3 seconds in each direction. Whenever an astronaut spoke a sentence into their radio microphone, the technicians and scientists back on Earth would not hear the audio for nearly 1 1/3 seconds. This occurred because the radio signals, which move at the maximum speed of light, required that precise amount of time just to cross the physical gap between the two worlds. Once the team at Mission Control listened to the message and spoke their reply, that audio response required another 1.3 seconds to travel back across space to reach the headphones of the astronauts on the Moon. As a direct result of this, every single verbal interaction between the two teams had an unavoidable built-in delay of nearly 3 seconds. If you listen closely to the original archival audio recordings of those historic space flights, you can clearly hear this specific pause. There is always a distinct lag present in the conversation, which serves as a real-time demonstration of the physical distance the radio signals had to cross, proving that absolutely nothing, not even data-carrying radio waves, can move through the universe faster than the speed of light. Stepping up the scale, we find that one single light minute consists of 60 light seconds, which calculates to a physical distance of 18 million kilometres. Our Sun is positioned roughly 8 light minutes away from the Earth, representing a total distance of approximately 150 million kilometres. This means that a single light minute is roughly equal to 12% of the total physical gap that separates the Earth from the Sun. If you could imagine a scenario where you were able to stand directly on the surface of the Sun, which is physically impossible because the Sun is a churning ball of superheated plasma with a surface temperature hovering around 5,500 degrees Celsius, you would look out at the Earth and see our planet exactly as it existed 8 minutes and 20 seconds in the past. If the Earth were to suddenly experience a catastrophic explosion right now, an observer on the Sun would remain completely unaware of the event for more than 8 minutes. The physical destruction would occur, but the light generated by that event, which carries the visual data across space, would still be mid-journey, taking more than 8 minutes to traverse the distance between the two celestial bodies. This reality creates very real and practical challenges for modern space exploration that the general public rarely considers. Whenever scientists at NASA operate robotic rovers on the surface of Mars, they must constantly contend with a significant communication delay caused by the immense distance to the red planet. At its absolute closest point, when the orbital paths of Earth and Mars align them on the exact same side of the Sun, Mars is situated roughly 56 million kilometres away from us, which translates to a light travel time of about 3 minutes. However, when the two planets travel to the opposite sides of the Sun, the physical gap widens to roughly 400 million kilometres, creating a light travel time of approximately 22 light minutes. This means that when their Perseverance rover is driving and exploring the Martian terrain, every single command broadcast from computers on Earth requires anywhere from a few minutes up to 22 minutes just to reach the rover's antenna, depending entirely on the shifting positions of the two worlds in their solar orbits. Likewise, any scientific data or images the rover transmits back into space require that exact same duration of time to reach receiving dishes on Earth. Because of this, it is completely impossible to operate a Martian rover in real time using a joystick, the way someone might operate a remote-controlled toy car on Earth. The time delay makes direct steering impossible. Instead, NASA engineers are forced to map out and program the rover's movements with extreme care well in advance. They spend hours analysing the landscape images captured on previous days, plot a precise driving path, write out a complex sequence of digital commands, upload those instructions to Mars, and then wait anxiously for the results. If the vehicle encounters an unexpected hazard, such as getting its wheels wedged against a sharp rock or sliding into a dangerous sand dune, the engineering team cannot intervene immediately to stop it. They must wait out the long window of time it takes for the telemetry data to reach Earth. Once they receive the alert, they must study the problem, engineer a viable solution, code a brand new set of corrective commands, transmit those signals across space, and wait another long delay to find out if the fix worked. A minor driving mistake that could be corrected in a fraction of a second on Earth can easily stretch into an intense hour-long operation when it happens on Mars. Moving further up our cosmic ladder, one single light hour is composed of 60 light minutes. This translates to an immense distance of about 1,080 million kilometres. At this scale, the numbers become so incredibly massive that trying to form a clear mental image of the distance becomes a genuine struggle. To put this unit into perspective, the planet Saturn, at its closest orbital approach to Earth, is situated roughly 1.2 light hours away from us. Saturn is the most distant planet in our solar system that a person can easily locate in the night sky using nothing but their naked eye. It is a stunning world famous for its majestic ring system, and humans have observed it since ancient times, yet it resides over a light hour away from our doorsteps. When the robotic Cassini spacecraft spent 13 years orbiting Saturn from 2004 until 2017, capturing thousands of historic close-up photographs of the gas giant and its diverse collection of moons, there was always an inherent delay of over an hour between the exact moment the camera snapped a picture and the moment that visual data arrived on Earth. The spacecraft would capture an image, convert the visual information into digital code, and beam that data through space as a radio signal moving at the speed of light. More than an hour later, deep space tracking antennas on Earth would finally intercept the signal so scientists could view the image. Because of this physical reality, the Cassini spacecraft could never be piloted in real time. Mission operators could not look at a live video feed and adjust the spacecraft's flight path on the fly to avoid unexpected hazards, the way a person might fly a modern drone. Instead, teams had to map out and program entire operational sequences days, or sometimes weeks, ahead of schedule. They would upload these massive blocks of commands to the spacecraft's onboard computer and place their full trust in Cassini's ability to execute the instructions flawlessly. If a critical error or system malfunction occurred during a maneuver, the spacecraft had to possess enough onboard artificial intelligence to detect the issue and switch itself into a protected safe mode automatically. This automated autonomy was mandatory because by the time the data warning of the failure travelled back to Earth, and a new set of troubleshooting commands was designed and beamed back to Saturn, more than 2 full hours would have elapsed. In that massive time window, the physical situation could have decayed completely. Stepping up to the next level, one light day is comprised of 24 light hours, which amounts to a staggering distance of roughly 25,900,000,000 kilometres. We are now venturing into regions of space where even the speediest machines ever engineered by human hands appear to move at a slow crawl by comparison. Consider Voyager 1, a legendary scientific probe launched into space in 1977. It holds the record as the most distant human-made object ever created. As of the year 2025, Voyager 1 is located roughly 24 light hours away from its home planet. The probe has been screaming through the absolute void of space for nearly 50 years, maintaining a constant velocity of approximately 17 kilometers per second, which translates to an incredible speed of over 61,200 kilometers per hour. By any terrestrial human standard, that speed is blindingly fast. Moving at 17 kilometers per second, you could travel from the Atlantic coast of the United States all the way to the Pacific coast in about 2 minutes flat. Yet, despite nearly 5 decades of uninterrupted flight through the vacuum of space, with absolutely no atmospheric friction to slow its momentum, Voyager 1 has still not managed to cover a single full light day of distance from Earth. This immense distance corresponds roughly to the location of the heliopause, which is the physical boundary zone where the dominant influence of our Sun drops away and true interstellar space begins. The heliopause is the region where the solar wind, the relentless high-speed stream of electrically charged particles blowing outward from the Sun in every direction, finally loses its forward momentum, slowing down as it collides and mingles with the cold interstellar medium. This interstellar medium is the incredibly thin, sparse gas and dust that fills the vast empty gaps separating the stars. Voyager 1 officially crossed this invisible cosmic boundary in the year 2012, cementing its place in history as the very first manufactured object to to exit our solar neighbourhood and enter the uncharted territory of interstellar space. While this achievement marked a historic milestone for human ingenuity and exploration, in the grander context of the cosmos, the spacecraft is still located within a single light day of our Sun. On a truly galactic scale, it remains parked right in our immediate backyard. If we scale upward to 1 light week, which is equal to 7 light days, we are looking at a physical span of approximately 181 billion kilometres. At this profound distance, we enter a dark, silent realm where no piece of human technology has ever travelled, and where no spacecraft will venture for many decades, or perhaps even centuries to come. This is the true deep void of space, positioned far beyond the orbits of the known planets and well past the limits of our direct exploration. If you were to travel out to this distance, the Sun would no longer dominate the sky as the blinding, brilliant sphere of life-giving light and intense heat that we experience from the surface of the Earth. Instead, from a distance of 1 light week, our parent star would shrink down until it looked like nothing more than an exceptionally bright star. It would certainly stand out as noticeably brighter than the other points of light around it, but it would ultimately appear as a solitary, compact dot of light hanging in an overwhelming ocean of pitch-black darkness. If you could somehow find a way to float suspended in the vacuum of space at this 1 light week marker and look back toward the centre of our solar system, you would witness the Sun as a brilliant stellar point. However, you would also see thousands of other distant stars boldly scattered across the dark velvet of the night sky. Gazing at this view, you would likely realise with deep clarity, for the very first time in your life, that our Sun is simply one ordinary star out of countless options. Moving outward to 1 light month, which equals roughly 30 light days of travel time, the physical distance swells to approximately 778 billion kilometres. If you were to set up a powerful telescope at this immense distance and point it back toward our Sun, the Sun would appear as an ordinary star, showing itself to be no brighter or more impressive than many of the other stars twinkling in the surrounding sky. The entire structure of our solar system, along with its planets, moons, rocky asteroid belts and icy comets, would be almost entirely invisible to the naked eye. Even if you used a highly sophisticated telescope, you might barely be able to resolve the planet Jupiter as a microscopic, dim speck of light, while the inner rocky worlds like Earth, Mars and Venus would be completely lost, swallowed up by the glare of the Sun. Everything that we define as our home solar system, all the planets we have spent generations studying, all the worlds where we have sent robotic emissaries, and all the environments we know, would be tightly compressed into a tiny patch of space surrounding an unremarkable star. Finally, we arrive at the full scale of 1 single light year, which is composed of 365 light days. This is equal to 12 light months, 52 light weeks, or 8,760 light hours. It breaks down into 525,600 light minutes, or a staggering 31,536,000 light seconds. Look closely at how rapidly these numbers multiply as we scale up our view. We initiated this mental exercise with a single light second, which was already an immense distance by human standards, spanning a gap that could cover a trip to the moon and back. From there, we continuously multiplied that distance by progressively larger numbers: 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, 30 days in a month, and 12 months in a year. Only after completing that entire multiplication process do we finally reach the baseline unit of 1 light year, which equals 9.46 trillion kilometres. This is the total physical distance that a beam of light can cross over the course of 1 full calendar year, assuming it travels at a constant speed of 300,000 kilometres every single second for 365 days without ever slowing down. This massive unit is the standard metric that astronomers rely on to map the gaps separating the stars because, across the universe, stars are isolated by these vast gulfs. Even if our species engineered ideal propulsion mechanisms with unfettered access to boundless energy reserves, and even if we managed to solve every conceivable technological obstacle blocking our path, we would still remain completely unable to travel at a velocity faster than light. The distance of 4.24 light-years separating our solar system from Proxima Centauri represents an absolute minimum journey time of 4.24 years. This reality remains unyielding even in the most wildly optimistic hypothetical situation where humans could somehow accelerate an interstellar vehicle to a speed that nearly matches the velocity of light. It is crucial to remember that this duration is just what is required to reach our absolute closest stellar neighbour. The vast majority of other interesting destinations scattered across the deep void of space are positioned much, much farther away from our planet. To bypass this rigid cosmic speed limit, some creators of science fiction have proposed highly imaginative concepts. They write about warp drives designed to physically distort the fabric of space surrounding a spacecraft, which would theoretically allow the vehicle to effectively arrive at its destination faster than a beam of light without ever actually moving faster than light through its local space. Other writers describe wormholes, which are imagined as stable tunnels or shortcuts puncturing the fabric of space-time to instantly link two highly distant points in the cosmos. Still others rely on the concept of hyperspace, a completely alternate dimension where the fundamental laws of physics function differently, making faster than light travel an everyday reality. These are incredibly creative ideas, and a few of them, such as the concept of a warp drive, actually possess a real foundation within modern theoretical physics. The Alcubierre drive, which was mathematically proposed by physicist Miguel Alcubierre in the year 1994, stands as a notable theoretical solution to Einstein's field equations. This mathematical model suggests that faster-than-light travel could technically be achieved by contracting the fabric of space directly in front of a spacecraft, while simultaneously expanding space behind it. However, translating these highly abstract mathematical concepts into a concrete piece of physical machinery presents obstacles that are completely mind-boggling. To construct an operational Alcubierre drive, engineers would need to acquire and manipulate vast quantities of exotic matter that possesses negative mass or negative energy. As far as modern scientific observation can tell, this type of matter may not even exist anywhere within the real universe, even if physicists eventually manage to prove that negative energy can exist in small amounts. The total quantity required to warp space around a human-scaled vehicle would be utterly immense, potentially equaling the mass-energy equivalent of an entire major planet. Furthermore, the intense gravitational forces and extreme radiation fields generated by distorting space-time in this manner would likely incinerate any human passengers riding inside the vehicle. It could also completely ablate any stellar systems or planets located at the journey's destination. Therefore, unless our fundamental understanding of physics experiences a radical and complete revolution, the speed of light will remain an absolute and unyielding barrier for human travel. When we look beyond our immediate cosmic neighbourhood and begin measuring distances to other stars, we quickly discover that space is incredibly empty. The vast majority of the universe consists of a profound vacuum, punctuated only occasionally by small islands of matter. To help visualise this loneliness, it is useful to scale our solar system down to a size that can fit within a standard room. If we imagine our sun shrunk down to the size of a small fruit, like an orange resting on a table in the centre of a room, the planet Earth would be a microscopic speck of dust orbiting roughly 15 meters away. The giant planet Jupiter would be about the size of a small marble, circling the orange at a distance of roughly 75 meters. The most distant known planet in our system, Neptune, would be a tiny grain of sand positioned nearly 450 meters away from the center table. On this exact same scale, the very nearest star to our Sun, Proxima Centauri, would be located thousands of kilometers away. The space between the fruit on the table and that distant star would contain absolutely nothing but empty air. This vivid visualization illustrates that stars are not tightly packed together like trees in a dense forest. Instead, they are solitary, isolated fireflies, separated from one another by deep oceans of absolute nothingness. Let us begin to explore the specific distances to some of the most famous stars in our night sky to see how these light years pile up. If we look toward the constellation of Canis Major, we can find Sirius, which is officially recognized as the brightest star visible in the entire night sky from Earth. Sirius is a brilliant blue-white star that burns with an intensity significantly greater than our Sun. It is located roughly 8.6 light-years away from us. This means that when you step outside at night and look up at Sirius, the photons of light entering your eye at that exact moment have been travelling through the cold vacuum of space for over 8.5 years. You are seeing the star precisely as it existed nearly a decade in the past. If Sirius were to suddenly stop burning right now, human observers on Earth would continue to see it shining brightly in the sky for another 8.6 years, completely unaware that its light source had vanished. Venturing slightly further out into our stellar neighbourhood, we encounter another incredibly famous star known as Vega. Located in the constellation of Lyra, Vega holds a special place in astronomy because it was one of the very first stars to have its photograph taken and its light spectrum analysed by early astronomers. Vega is situated approximately 25 light-years away from Earth. This distance introduces a fascinating historical perspective to our observation. When the light you see from Vega tonight first left its hot stellar surface, a quarter of a century had not yet passed on Earth. Depending on the current calendar year, that light may have began its journey around the turn of the millennium or during the late 1990s. The photons were already racing across the universe, while humanity was entering a new century, developing the modern internet and launching early smartphones. All of modern digital history has unfolded on Earth, while that light was quietly making its way across space to reach your eyes. If we continue to climb the cosmic ladder, we reach Aldebaran, a massive red giant star located in the zodiac constellation of Taurus. Aldebaran is often referred to as the Eye of the Bull because of its distinct, fiery reddish-orange appearance in the night sky. This aging star has expanded to a size that is dozens of times larger than our Sun, and it is located roughly 65 light-years away from us. When the light from Aldebaran that arrives on Earth tonight first began its journey, the world was in the midst of the mid-20th century. Major historical events like the space race were just beginning, and human beings had not yet walked on the surface of the moon. The entire modern world we inhabit today was still decades away from existing when those specific photons began travelling toward our planet. Moving even deeper into the galaxy, we find Rigel, a spectacular blue supergiant star that forms the brilliant left foot of the constellation Orion. Rigel is an absolute monster of a star, radiating tens of thousands of times more energy than our Sun. It is located roughly 860 light-years away from Earth. Because of this immense distance, when you look at Rigel in the winter sky, you are looking back into the deep history of human civilization. The light entering your eye tonight left Rigel during the High Middle Ages on Earth. During the era that those photons were beginning their long trip across the interstellar void, European builders were just starting to construct great stone cathedrals, and the Mongol Empire had not yet swept across Asia. Generations of humans have lived, fought and died. Entire empires have risen and turned to dust, and our technology has advanced from wooden carts to space telescopes, all during the time it took for a single beam of light to travel from Rigel to Earth. Not far from Rigel, in the sky sits Betelgeuse, another supergiant star that marks the right shoulder of Orion. Unlike the crisp blue Rigel, Betelgeuse is a semi-regular variable red supergiant that is approaching the absolute end of its life cycle. It has bloated to such an immense size that if you were to place it in the centre of our solar system, where the Sun sits, its outer atmosphere would swallow up the orbits of Mercury, Venus, Earth, Mars, and would reach all the way out to Jupiter. Betelgeuse is located approximately 640 light-years away from us. Astronomers know that because Betelgeuse has exhausted its primary nuclear fuel, it is destined to die in a spectacular supernova explosion sometime within the next 100,000 years. In fact, because the star is 640 light-years away, it is entirely possible that Betelgeuse has already exploded. The star could have run out of fuel and shattered itself centuries ago, but the visual data of that explosion is still mid-journey. The light carrying the image of its destruction could be travelling through space right now, and we will not discover the truth until that light finally crosses the finish line and hits Earth. Let us now look toward the northern sky to locate Polaris, commonly known as the North Star. For thousands of years, Polaris has served as a critical navigation aid for sailors, explorers and travellers because it sits almost perfectly aligned with the Earth's northern rotational axis. While it appears to remain stationary in the sky while other stars rotate around it, Polaris is located roughly 433 light-years away from Earth. When the current light from Polaris began travelling toward us, the first permanent English colonies in North America had not yet been established. The historic settlement of Jamestown would not be founded for another 12 years, and the Pilgrims would not arrive at Plymouth Rock for another 26 years. Famous historical figures like William Shakespeare were just beginning to write their very first plays. He had produced some of his earliest works, but he had not yet written his masterpieces like Hamlet, Macbeth, or King Lear. The United States would not exist as a nation for another 180 years. When that light from Polaris began its long journey, human society was fundamentally different from what we know today. Tonight, that ancient light finally completes its trip and enters your eye, connecting you directly across space and time by photons that have been travelling since the Renaissance. Within a relatively small bubble of about 20 light-years surrounding the Earth, astronomers have identified approximately 130 known star systems. Some of these systems consist of single, isolated stars, just like our Sun. Others exist as binary systems where two distinct stars are locked in a gravitational dance, orbiting around a common centre of mass. There are even triple star systems, such as Alpha Centauri, which features 3 stars bound together by gravity. Developing a deep understanding of this immediate stellar neighbourhood helps us appreciate both the scale of the distances involved and the incredible variety of stars that exist right in our cosmic backyard. Among these nearby neighbours, Barnard's Star stands out as an object of great scientific interest. Located roughly 6 light-years away from Earth, it is the second closest star system to us, after the Alpha Centauri trio. Barnard's Star is a red dwarf, which means it is much smaller, cooler, and significantly dimmer than our Sun. What makes Barnard's Star particularly fascinating to astronomers is its exceptionally high velocity relative to our solar system. It possesses the largest proper motion of any known star in the entire sky, meaning that it changes its position across the background of space faster than any other star observed from Earth. Over the course of just a few decades or centuries, careful tracking allows us to easily see Barnard's star shifting its location relative to more distant stars. In about 10,000 years, its forward motion will bring it closer to Earth than Proxima Centauri is today, making it our brand new nearest stellar neighbour. However, even at its absolute closest approach to us, it will still be situated nearly 4 light years away. The distance separating stars are so incredibly vast that even when objects are screaming toward each other at high speeds, it still requires thousands of years for that motion to make a meaningful difference in the total distance between them. Further out in our immediate neighbourhood sits Wolf 359, located about 7.9 light years away from Earth. This star is another faint red dwarf, so dim that it cannot be seen without the aid of a powerful telescope. Despite its small size, it has captured the imagination of science fiction writers for decades, frequently serving as a setting for fictional space battles and alien encounters. The reality of Wolf 359 is a quiet, slow-burning star that will likely outlive our Sun by trillions of years, because small red dwarfs consume their hydrogen fuel at an incredibly slow pace. As we move past individual neighbouring stars and look at the broader organisation of space, we begin to find planetary systems orbiting these distant suns. One of the most remarkable discoveries of modern astronomy is the TRAPPIST-1 system, located roughly 40 light years away in the constellation of Aquarius. TRAPPIST-1 is an ultra-cool red dwarf star that is home to a staggering 7 rocky Earth-sized planets. This represents the largest number of rocky planets ever discovered orbiting a single star outside of our solar system, because red dwarfs are the most common type of star in our galaxy, making up roughly 70% of the total stellar population. The discovery of the TRAPPIST-1 system strongly suggests that rocky terrestrial worlds might be incredibly common throughout the universe. The architecture of the TRAPPIST-1 system is remarkably compact. All 7 of its planets orbit incredibly close to their parent star, with their entire orbital paths fitting comfortably within a distance that is much smaller than the orbit of Mercury around our Sun. However, because the central star is so small and emits far less heat than our Sun, 3 of these tightly packed planets sit directly within the star's habitable zone. This means they receive an amount of stellar energy that is roughly comparable to what Earth receives from the Sun, allowing for the theoretical possibility of liquid water existing on their surfaces. If you could somehow stand on the surface of one of these worlds and look up at the sky, you would witness an extraordinary view. The neighbouring planets would be clearly visible to your naked eye, with some appearing much larger in the sky than our Moon appears from Earth. Because the planets are positioned so close together, travelling from one world to the next would be far easier and require significantly less time than travelling between the planets in our own solar system. When we observe the TRAPPIST-1 system through modern telescopes today, we are seeing the system exactly as it existed 40 years ago, back in the mid-1980s. If intelligent life has managed to emerge on one of those 7 planets, and if that civilization developed radio technology and began broadcasting signals out into the void of space, those radio signals would require a full 40 years just to reach Earth. We would be receiving their historic broadcast today. If we detected such a signal this evening and immediately transmitted a radio response back toward them, it would take another 40 years for our message to cross the gulf of space. The alien astronomers would finally receive our reply another 40 years later. This creates an 80-year round trip just to complete a single basic exchange of information. A human scientist on Earth could ask a simple question to the alien civilization as a young adult and pass away from old age before the answer ever arrived. Thinking deeply about this reality forces us to re-evaluate what communication truly means when distances are measured in light years. This is one of the most challenging and sobering aspects of cosmic scaling, and it carries profound implications for any future where humanity attempts to establish permanent settlements on other worlds or make lasting contact with intelligent extraterrestrial civilizations. Radio waves move through space at the exact speed of light. They are a form of electromagnetic radiation, identical to the visible light we see with our eyes, but characterized by much longer wavelengths. When we broadcast radio signals from our communication dishes into space, they expand outward in all directions at a speed of 300,000 kilometers every single second. But even at this ultimate speed limit, communication across light years remains a painstakingly slow process. Consider our most distant explorer, the Voyager 1 spacecraft, which is now located roughly 24 light hours away from Earth. This distance creates a communication delay of about 24 hours in each direction. When mission controllers at NASA transmit a digital command to Voyager, that signal requires a full day just to reach the spacecraft's antenna. The radio signal moves at light speed, covering roughly 25 billion kilometers of space to reach its target. Once Voyager receives the instruction and transmits its data back, that signal requires another 24 hours to make the return trip to Earth. This means there is an unavoidable 48-hour delay for any two-way interaction. If a critical malfunction occurs on the spacecraft, Voyager must rely entirely on its onboard automated systems to diagnose and resolve the issue. By the time the warning data travels back to Earth and engineers write a solution, 2 full days have passed, and the physical state of the spacecraft could have changed completely. A similar challenge was experienced by the New Horizons spacecraft during its historic flyby of Pluto. When the probe zoomed past the icy dwarf planet, it was located billions of kilometers away, creating a one-way light travel time of several hours. The spacecraft had to execute its complex science imaging sequence completely autonomously because real-time steering from Earth was completely out of the question due to the immense communication lag. When we scale our gaze outward beyond nearby star systems and planetary systems, we begin to see the true structure of our home galaxy, the Milky Way. The Milky Way is a colossal barred spiral galaxy, a swirling disk composed of hundreds of billions of stars, vast clouds of gas, and lanes of cosmic dust, all rotating around a supermassive black hole located at the galactic center. The physical size of this stellar structure is difficult to comprehend. To measure the galaxy, astronomers must abandon smaller units entirely and rely strictly on light years. The disk of the Milky Way spans approximately 100,000 light years from one edge to the other. Think about this scale for a moment. If a beam of light is emitted from a star located at the absolute outer edge of the galaxy, it must travel through space for 100,000 years just to reach the opposite side. Our Sun is located nowhere near the center of this majestic structure. Instead, we reside in a relatively quiet region of the galaxy, nestled within the inner edge of the Orion Arm, one of the spiral structures radiating outward from the galactic center. We are positioned roughly 26,000 light years away from the supermassive black hole known as Sagittarius A that sits at the core of the galaxy. This means that when astronomers point powerful infrared telescopes toward the center of the Milky Way to observe the stars orbiting the central black hole, they are viewing light that left that chaotic region 26,000 years ago. That light began its journey toward Earth during the height of the last ice age, long before the dawn of human civilization. When we try to study the shape and size of our home galaxy, we run into a major problem because we are trapped inside it. We cannot take a spaceship and travel far above the galactic disk to look down and snap a clear photograph of its beautiful spiral structure. Everything we know about the Milky Way must be learned by looking out through the layers of stars and dust from our position within the disk. Despite this limitation, astronomers have used clever measurements to map our surroundings with incredible accuracy. Because it is impossible to see the entire galaxy from a single viewpoint, scientists must rely on indirect tracking methods, analysing the light and movements of distant stars to calculate its overall form. The best current estimates made by modern astrophysicists suggest that the Milky Way contains somewhere between 100 billion and 400 billion individual stars. The most widely accepted number among experts settles around 200 billion to 300 billion stars. This is an absolutely staggering population of suns, and each one represents a unique place in the cosmos. Our own sun is just a single ordinary member of this massive stellar city. It is classified as a typical yellow dwarf star of completely average size, mass and brightness. There is absolutely nothing special or unique about our Sun when you look at it from a broad galactic perspective. It is not the largest star in the galaxy, nor is it the brightest or hottest. Similarly, it is not the coolest or the smallest. It is simply a standard, routine star sitting among hundreds of billions of other routine stars. Our Sun is positioned within one of the smaller structural arms of the galaxy, known as the Orion Arm or the Orion Spur. This arm is situated between two much larger spiral structures, the Perseus Arm and the Sagittarius Arm. We are located roughly 26,000 light years away from the chaotic galactic centre, where a supermassive black hole resides. This means the light we see from the central core of our galaxy today actually left that region 26,000 years ago, travelling through deep space since the days when early humans were surviving the last ice age. As we look around our stellar neighbourhood, we find that stars are not the only things filling the galaxy. Most of these suns are accompanied by their own families of worlds. One of the most spectacular examples of an alien solar system ever found is the TRAPPIST-1 system, which sits roughly 40 light years away from Earth in the constellation of Aquarius. The central star of this system is an ultra-cool red dwarf. Because red dwarfs are the most common type of star in the Milky Way, accounting for approximately 70% of the total stellar population, studying them is critical to understanding the universe. The discovery of TRAPPIST-1 was a major milestone because astronomers found a staggering 7 rocky Earth-sized planets orbiting this single small star. This discovery strongly suggests that terrestrial rocky worlds might be incredibly common throughout our galaxy and the wider universe. The physical layout of the TRAPPIST-1 system is remarkably compact and crowded compared to our own solar system. All 7 of these planets are packed tightly together, orbiting so close to their parent star that their entire orbital paths would fit comfortably inside the orbit of Mercury around our Sun. However, because an ultra-cool red dwarf is much smaller and emits far less heat and light than our Sun, its planets do not burn up despite their close proximity. In fact, 3 of these 7 closely packed planets receive an amount of energy that places them directly within the star's habitable zone. This means their surface temperatures could theoretically allow for the existence of liquid water, which is the primary ingredient required for life as we know it. If you could somehow stand on the surface of one of these alien worlds and look up at the daytime sky, you would be treated to a breathtaking view. The neighbouring planets would be clearly visible to your naked eye, appearing as large, detailed spheres in the sky, with some looking significantly larger than our Moon appears from Earth. Because these worlds are positioned so close to one another, travelling between them would require far less time and energy than travelling between the planets in our own system. When we observe the TRAPPIST-1 system through modern telescopes, we are not looking at it as it exists right now in the present moment. Because it is located 40 light years away, we are seeing the system exactly as it was 40 years ago, back in the mid-1980s. The photons of light that enter our instruments today have spent 4 decades crossing the cold vacuum of space to reach us. This introduces a fascinating and sobering reality regarding communication across interstellar distances. If intelligent life has managed to evolve on one of those 7 worlds, and if that civilization developed radio communication and began broadcasting signals out into space, those radio signals would take 40 years to reach Earth. We would just now be receiving broadcasts that they transmitted decades ago. If human scientists detected that alien signal tonight and immediately sent a radio response back toward TRAPPIST-1, our message would require another 40 years to make the return trip. The alien observers would not receive our reply for another 4 decades. This creates a minimum 80-year round-trip delay just to complete a single, basic exchange of information. A young human scientist could dedicate their early career to sending a message to this neighbouring system and pass away from old age before the response ever arrived. This incredible lag forces us to completely re-evaluate what communication truly means when distances are measured using light years. It highlights one of the most challenging and isolating realities of cosmic scales, carrying profound implications for any future where humanity attempts to build permanent colonies on other worlds or establish meaningful contact with extraterrestrial civilizations. Radio waves move through space at the exact speed of light. They are a form of electromagnetic radiation, fundamentally identical to the visible light we see with our eyes, but characterized by much longer wavelengths. When we transmit radio signals from our communication dishes into the void, they expand outward at a speed of 300,000 kilometers every single second. But even at this ultimate cosmic speed limit, communication across light years is a painfully slow and delayed process. To see this delay in action closer to home, we can look at our most distant robotic explorers. The Voyager 1 spacecraft, which was launched from Earth in the year 1977, is currently the most distant human-made object in existence. It has been travelling away from us for nearly 50 years, moving through the vacuum of space at an incredible speed of roughly 17 kilometers per second, which translates to over 61,000 kilometers per hour. This speed is fast enough to travel from one coast of the United States to the other in just about 2 minutes. Yet, despite half a century of constant uninterrupted travel through space with absolutely nothing to slow it down, Voyager 1 is only about 24 light hours away from Earth. It has not even managed to cover a single light day of distance. When mission controllers at NASA transmit a command to Voyager 1, the radio signal requires a full 24 hours just to reach the spacecraft's antenna. The signal travels at the speed of light, crossing approximately 25 billion kilometers of space. Once Voyager receives the instruction and sends its data back, that return signal requires another 24 hours to reach Earth, creating a 48-hour delay for any two-way interaction. Because of this inescapable delay, real-time control of the spacecraft is completely impossible. If a critical hardware failure or software anomaly occurs on Voyager, the spacecraft cannot wait for human intervention. It must rely entirely on its onboard automated programming to diagnose the problem, protect its systems, and switch to a safe mode autonomously. By the time the warning data travels across space to alert engineers on Earth, and by the time those engineers write a solution and transmit it back, 2 full days have passed. In that time, the physical state of the spacecraft could have changed completely, or the vehicle could be lost entirely. A similar communication challenge was faced by the New Horizons spacecraft during its historic flyby of Pluto. When the probe arrived at the outer edges of our solar system, it was located billions of kilometres away from Earth, creating a one-way light travel time of several hours. The spacecraft had to execute its highly complex scientific imaging sequence completely autonomously because sending real-time steering commands from Earth was impossible due to the immense communication lag. When we expand our view outward beyond individual stars, planetary systems, and the confines of our own galaxy, we enter the realm of the truly immense. The Milky Way is just one galaxy among many, and it belongs to a small cluster of galaxies known as the local group. The local group contains more than 50 individual galaxies, most of which are small dwarf galaxies orbiting the two dominant members of the group, the Milky Way and the Andromeda Galaxy. The Andromeda Galaxy, also known as M31, is our nearest large galactic neighbour. It is a massive spiral galaxy, slightly larger than the Milky Way, and it is located roughly 2.5 million light-years away from us. When you look up at the night sky and locate the faint, blurry smudge of the Andromeda Galaxy with your naked eye or a pair of binoculars, you are looking at light that has been travelling through intergalactic space for 2.5 million years. That light left its home stars long before modern human beings existed on Earth, during a time when our distant hominid ancestors were first learning to use primitive stone tools. As we look even further into the deep universe, the scales become completely mind-boggling. Beyond the local group lies the Laniakea supercluster, an immense cosmic structure that spans roughly 500 million light-years across and contains more than 100,000 individual galaxies. Our galaxy is just a microscopic speck tucked away inside one small branch of this colossal network. To measure structures of this scale, astronomers must track the light from galaxies that has travelled for hundreds of millions or even billions of years to reach our telescopes. This brings us to the concept of the observable universe, which represents the total sphere of space that human beings can theoretically see from Earth. The universe is estimated to be approximately 13.8 billion years old, meaning that light has had 13.5 billion years to travel since the Big Bang. However, because space itself has been continuously expanding while that light was travelling toward us, the edge of the observable universe is much farther away than 13.8 billion light years. Today, the radius of the observable universe is calculated to be roughly 46.5 billion light years, making the entire observable sphere span a staggering 93 billion light years from one side to the other. This 93 billion light year sphere represents the absolute physical limit of what human beings can ever see or interact with. Beyond this boundary lies the cosmic horizon. Space beyond our horizon is expanding away from us at a rate that effectively exceeds the speed of light, meaning the light emitted from those ultra-distant regions will never have enough time to cross the expanding gap to reach Earth. It does not matter how powerful our future telescopes become or how advanced our technology grows. The light from beyond the cosmic horizon is permanently cut off from us. It is lost to our view forever due to the fundamental geometry and expansion of space-time. Within the boundaries of our single observable universe, astronomers estimate that there are approximately 2 trillion individual galaxies scattered across space. Each one of those 2 trillion galaxies contains its own population of billions or even trillions of stars. If you multiply these estimates together, the total number of stars existing within the observable universe reaches a number that is completely incomprehensible to the human brain. roughly 200 billion trillion stars. That is a 2 followed by 23 zeros. Based on modern observations of planets orbiting nearby stars, we now know that planetary systems are the rule rather than the exception. Most stars host at least one planet, meaning there are likely just as many planets, if not more, scattered throughout the cosmos. The universe is absolutely filled with a near infinite number of worlds, more planets than we could ever hope to count, map or visit, even if humanity possessed unlimited time and perfect, magical technology. At these ultimate cosmic scales, the universe reveals a complex and beautiful structure known as the cosmic web. Galaxies are not just thrown randomly through empty space like grains of sand dropped on a floor. Instead, they are highly organised into distinct patterns, held together by the invisible pull of gravity. Galaxies gather together into clusters, which are groups containing hundreds or thousands of individual galaxies locked in a gravitational embrace. These clusters are further organised into even larger structures called superclusters, which represent massive concentrations of matter containing multiple distinct galaxy clusters. These superclusters are arranged in long, thin, interconnected threads called galactic filaments. These filaments form immense bridge-like structures of stars and galaxies that stretch across hundreds of millions of light-years of space. Woven between these dense galactic filaments are the cosmic voids. Voids are colossal, incredibly empty regions of space that contain almost no galaxies or matter at all. These vast bubbles of absolute loneliness can span hundreds of millions of light years across, forming deep oceans of nothingness that separate the crowded filaments of the cosmic web from one another. As we observe this vast web, we must remember that the universe is not static, it is actively expanding. Space itself is stretching out in all directions, carrying entire galaxies and clusters along with it, much like raisins embedded in a loaf of bread dough as it rises in an oven. This expansion does not mean that galaxies are simply flying through space away from each other. Rather, it means that the physical fabric of space itself is expanding, creating entirely new space between distant cosmic objects. For objects that are relatively close to one another, this universal expansion is completely negligible because it is easily overwhelmed by stronger fundamental forces. For example, the space separating the Earth and the Moon is not expanding in any meaningful way because the local pull of gravity firmly locks them together. Similarly, the space inside our solar system is stable because the Sun's gravity holds the planets securely in their orbits. Even the space within our own Milky Way Galaxy remains bound together by the collective gravity of its billions of stars and dark matter. Human beings can communicate across short distances almost instantly, taking immediate back and forth conversation completely for granted. However, when we try to communicate across the immense gulfs of interstellar space, this routine feature of human life becomes completely impossible. Any meaningful conversation between intelligent entities separated by light years is doomed to be painfully, frustratingly slow. A basic exchange of ideas or arguments would not take minutes or hours. Instead, it would stretch across entire human decades. If Earth were to enter into a critical diplomatic negotiation with a newly established colony orbiting Proxima Centauri, resolving even a single minor dispute could easily require a century or more of continuous effort. Each individual party would be forced to carefully deliberate, draft, and refine their responses, knowing with absolute certainty that several years would pass before their message even reached its destination, and years more would slip away before a reply could possibly be returned to them. This inescapable communication lag carries profound and unsettling implications for the future of human governance, politics, and the basic structure of society. far exceeding a simple logistical inconvenience. If humanity eventually manages to plant a permanent settlement on an alien planet situated 4 light years away, that colony could never be governed, managed or directed from Earth in any real or meaningful capacity. Any emergency laws, political directives or administrative decrees transmitted from our home world would inevitably arrive at their destination years out of date, rendered entirely obsolete by the passage of time. The shifting political landscapes, revolutions or institutional changes unfolding on Earth could fundamentally alter or completely overturn the home government between the precise moment a message was broadcast into the void and the moment it finally reached the colony's receivers. By the time the distant settlers received official orders from their planetary home, those orders might be completely irrelevant, representing policies of a government that no longer exists or has completely changed its objectives. Consequently, any interstellar colony would be forced to maintain absolute autonomy, operating with total independence from Earth. The settlers would have to possess the full authority and capability to make their own critical decisions regarding every single aspect of their daily survival, from the micromanagement of resource allocation and agricultural production to complex conflict resolution and immediate emergency responses. Waiting for official approval, legal guidance or technical assistance from Earth on any major matter would be a practical impossibility that could result in the death of the colony. Because of this profound physical isolation, the human colony and our home planet would inevitably begin to drift apart culturally over the course of successive generations. They would slowly develop their own unique language dialects, their own distinct social customs, their own moral systems, and their own innovative ways of solving everyday problems. They would remain connected to Earth only by historical data streams, receiving electronic letters dispatched from a distant past, but they would be entirely unable to maintain the immediate, real-time social connections that hold human civilizations together. Over centuries, the populations of both worlds might diverge so radically that they would barely recognize each other as belonging to the same culture or society. When we turn our gaze away from our immediate neighbourhood and look up at the thousands of stars visible in a clear night sky, we are looking at a vast collection of unique cosmic histories. Every single star burning in the dark void has its own specific narrative of birth, life, and eventual death. Some of these objects are incredibly young, currently forming from the gravitational collapse of massive, swirling clouds of interstellar gas and dust, just beginning their lives as roaring nuclear furnaces. Others are middle-aged and stable, much like our own sun, steadily and reliably fusing hydrogen fuel inside their high-pressure cores to ensure a long, peaceful existence spanning billions of years. Still others are ancient, rapidly approaching the inevitable end of their life cycles after completely exhausting their primary nuclear fuel reserves. These dying suns are destined to collapse quietly into white dwarfs, cooling down over trillions of years, or to tear themselves apart in spectacular supernova explosions that scatter their heavy elements across space, recycling their matter to form future generations of stars, planets, and perhaps, eventually, living organisms. Yet, despite their shared physical laws and materials, every one of these stars remains deeply isolated from its neighbours, separated by oceans of absolute darkness that require light itself years to cross. The universe is a profoundly empty place, characterised by small, isolated islands of brilliant light drifting within vast, silent deserts of nothingness. Even so, these lonely islands remain fundamentally connected to one another through the laws of gravity, the mechanics of light, and the shared history of their matter. The very atoms that make up our bodies, our world, and our neighbouring planets were originally forged inside the crushing hearts of long-dead generations of stars, which exploded and scattered their remains across the galaxy to be recycled into our solar system. As modern human technology continues to advance at an exponential rate, our capacity to measure these staggering interstellar distances and analyse these distant suns with extreme precision is reaching unprecedented heights. A prime example of this technological leap is the European Space Agency's Gaia spacecraft, which is currently operating in space to build the most sophisticated, precise and comprehensive three-dimensional map of our galaxy ever attempted by humanity. Gaia is continuously measuring the exact positions, distances and proper motions of more than 1 billion individual stars across the Milky Way. Alongside Gaia, our next-generation space observatories are allowing astronomers to pierce deeper into the cosmic past than ever before. The James Webb Space Telescope is actively detecting and imaging incredibly primitive galaxies whose light has been travelling through the expanding universe for over 13 billion light years, allowing us to view structures that existed near the very dawn of time itself. Future space observatories will undoubtedly push this boundary even further, capturing light emitted closer and closer to the Big Bang. Simultaneously, our ongoing search for worlds orbiting other suns is expanding our cosmic inventory at a dizzying pace. Astronomers have confirmed the existence of over 5,000 distinct exoplanets scattered throughout our region of the galaxy, with thousands of additional planet candidates waiting for official confirmation. Many of these newly discovered worlds are situated dozens, hundreds, or even thousands of light years away from Earth. We are actively mapping the geometry of these distant systems, identifying their atmospheric compositions, and hunting for potential signs of life. In the coming centuries, humanity might even attempt to launch our very first robotic exploratory probes to investigate nearby star systems directly. Proposals like the Breakthrough Starshot initiative suggest using ultra-powerful ground-based lasers to accelerate fleets of micro-spacecraft carrying sail technology to roughly 20% of the speed of light. This would theoretically allow the probes to cover the distance to Proxima Centauri in approximately 20 years. Yet, even if this highly ambitious engineering feat succeeds completely, the laws of physics dictate that the data collected by the probes would still require over 4 full years to travel across the void as radio signals to reach our dishes on Earth. Barring a radical, unimaginable revolution in our fundamental understanding of physics, the finite speed of light will remain an absolute and unyielding barrier for human exploration. The vast distances separating the stars cannot be engineered away. They are a fundamental, built-in property of the universe we inhabit. Understanding the true meaning of a light year fundamentally transforms how we perceive our species' position within the grand design of the cosmos, forcing us to confront profound questions about the long-term future of humanity and our ultimate relationship with outer space. These are not merely abstract, detached philosophical riddles meant for academic debate. They possess immediate real-world implications for how we strategize space exploration, how we conduct the search for extraterrestrial intelligence, and how we plan for the long-term survival of our species. For the vast majority of recorded human history, the universe was perceived as something small, intimate, and comforting. Ancient civilizations believed that the stars were simply tiny points of light attached to a rigid, rotating celestial sphere situated just beyond the orbits of the Moon and the local planets. The entire cosmos was thought to be contained within a highly restricted, accessible space that a human being could theoretically touch if they could somehow climb a high enough mountain or build a tall enough tower, Even when early modern astronomers finally realised that the stars were actually independent, distant suns scattered through space, humanity still possessed absolutely no intuitive concept of just how far away those objects truly were. Scientists guessed distances in millions or billions of kilometres, but the numbers remained completely abstract and unmeasurable, serving as undefined symbols rather than true indicators of scale. It was not until the early decades of the 20th century that astronomers finally developed the tools and methods required to accurately calculate the distance to other stars, revealing the terrifying emptiness of space. When astronomer Harlow Shapley measured the physical dimensions of the Milky Way Galaxy in the year 1918, demonstrating that our stellar city spanned a staggering 100,000 light-years from edge to edge, the global scientific community was deeply shocked. The universe was suddenly revealed to be thousands of times larger than any human being had ever dared to imagine. A few years later, in 1929, Edwin Hubble shook the foundations of science once again by proving that the mysterious spiral clouds observed in telescopes were not small gas clouds inside our own galaxy, but were entirely independent, distant galaxies positioned millions of light years away from us. In a single stroke, the known universe expanded outward by multiple orders of magnitude. Humanity went from believing that the Milky Way comprised the entirety of existence to realizing that our massive galaxy was merely one ordinary island drifting among billions of other galaxies scattered across a boundless cosmic ocean. Today, modern astrophysical measurements tell us that the observable universe spans an incredible 93 billion light-years across and contains at least 2 trillion individual galaxies. This is a number so completely gargantuan that it ceases to hold any practical meaning for our daily lives. Yet, it represents a real, concrete physical environment that completely surrounds our planet. No matter which direction you look into the night sky, if your eyes possess the power to see far enough without limitation, you would witness endless highways of galaxies stretching away into the deep distance, cluster after cluster, filament after filament, until your line of sight finally struck the absolute edge of the observable universe, where the light emitted by ancient matter simply has not had enough time to reach our planet since the beginning of time. This profound realization shifts human perspective in a deeply fundamental way. It forces us to accept that we do not occupy the center of the universe, and we are not special or unique in any structural cosmic sense. We live out our lives on a completely typical planet, orbiting an ordinary star, located inside a standard galaxy, tucked away in a routine, unexceptional corner of deep space. There is absolutely nothing geographically unique or privileged about our position in the cosmos. If a traveller was suddenly transported to a completely different galaxy, situated billions of light years away from Earth, they would be greeted by an almost identical cosmic view. They would see galaxies in every single direction, stretching away to a distant cosmic horizon, because the universe looks roughly uniform from every single vantage point. This scientific truth is simultaneously deeply humbling and profoundly empowering. It is humbling because it illustrates our utter insignificance in cosmic terms. The entire collective history of human civilization, everything our species has ever achieved, every war fought, every empire built, every technology invented, and every discovery recorded, has occurred on a single, fragile planet floating in a tiny, obscure corner of an average galaxy. From a broad cosmic perspective, the entire existence of humanity barely registers as a footnote. We are very much like microscopic bacteria living out their entire lives inside a single drop of water, completely oblivious to the vast, roaring ocean that surrounds them on all sides. Yet, this reality is also incredibly empowering because it demonstrates the astonishing capability of the human mind. Despite our physical smallness, we figured this out. We did not remain blind. We managed to measure these staggering distances, decode the laws of physics, and understand our true position within the cosmos. We built telescopes, launched spacecraft, and devised complex mathematical equations that allow us to peer across billions of light years to map the universe. We are physically tiny, but we are conscious entities capable of observing and understanding the very universe that created us. Understanding the reality of light years forces us to confront difficult, uncomfortable truths regarding interstellar travel and our future survival beyond the solar system. The distances separating us from other suns are so completely immense that they may represent absolute, unbreakable physical barriers that no amount of advanced technology can ever truly overcome. Consider the monumental effort required to send a crew of human astronauts to our absolute closest neighbouring star, Proxima Centauri, which sits 4.24 light years away. Utilising our fastest modern spacecraft technology, which peaks at roughly 192 kilometres per second, it would require approximately 6,800 years to complete the journey to this nearest neighbour. This duration is longer than the entirety of recorded human history. If our ancestors had launched an exploratory spacecraft to Proxima Centauri at the exact moment humans first invented writing in ancient Mesopotamia, that spacecraft would still be travelling through the cold void today, thousands of years away from reaching its destination. To make interstellar travel practical or achievable within a human lifetime, we would need to construct propulsion systems capable of moving exponentially faster. Even if engineers eventually design revolutionary new propulsion systems that allow a starship to travel at an incredible 10% of the speed of light, a feat that remains far beyond our current capabilities, the journey to Proxima Centauri would still require over 42 years of continuous travel. That single trip would consume the entire duration of a typical human career, stretching from early adulthood to retirement age. And remember, this is just to reach the absolute closest star to Earth. The vast majority of other interesting stars and exoplanets are located hundreds or thousands of times farther away. The engineering and biological challenges associated with such a decades-long voyage are completely terrifying. An interstellar vessel would require an absolutely immense amount of energy just to accelerate its mass to a significant fraction of light speed, and an equal amount of energy to slow down upon arrival. During the long journey through deep space, the vessel would need to protect its human crew from deadly cosmic radiation and constant bombardment by high-energy particles. The ship's life support systems would have to function flawlessly without failure or external replenishment for multiple decades. Furthermore, psychologists would have to contend with the profound, devastating psychological impacts inflicted on human beings confined inside a small metallic habitat for nearly their entire lives, completely cut off from Earth, surrounded by an absolute vacuum, travelling toward a destination they might not even live to see. To bypass these lifetime constraints, some futurists had proposed the concept of multi-generational ships. These would be colossal, self-sustaining ark ships designed to support populations of hundreds or thousands of humans for the centuries or millennia required to cross the gulf between stars. The individuals who finally arrive at the destination planet would be the distant descendants of the original crew who launched from Earth. These travellers would have been born on the ship, would live their entire lives within its metallic walls, and would finally step onto an alien world they had only heard about in ancient historical records and bedtime stories. The starship would function as a miniature, wandering human civilization completely severed from Earth, evolving its own independent culture, language, and social structures during the long voyage through the darkness. However, the execution of a multi-generational mission introduces extreme practical and ethical dilemmas. How do engineers maintain a perfectly closed artificial ecosystem for hundreds of years without catastrophic resource degradation or soil failure? How do you prevent severe genetic disorders from devouring a small, isolated population over multiple generations without fresh genetic material? How can you guarantee that the distant descendants will still want to dedicate their lives to completing a mission initiated by ancestors they never knew? What happens if 3 generations into the voyage, the ship's population holds a vote and decides they want to turn the vessel around and return to Earth? What if a sudden disaster, a mechanical failure, or a deadly plague sweeps through the enclosed habitats and wipes out the population? There would be absolutely no rescue mission coming to save them. They would be isolated light years away from any possible human help, drifting alone in the deep void. As an alternative to generation ships, other scientists have suggested the development of suspended animation or cryogenic freezing technology, where the human crew would be placed into a deep metabolic slumber for the duration of the interstellar voyage, to be automatically awakened by onboard computers upon arrival at the destination. If this technology could be perfected, it would elegantly resolve many of our greatest interstellar travel dilemmas. A frozen crew would require almost no active life support resources, eliminating the need for massive agricultural habitats. It would completely prevent the severe psychological trauma associated with long-term confinement, and it would entirely eliminate generational drift or shifts in mission objectives. Unfortunately, we currently have absolutely no idea if true cryogenic freezing is biologically possible for human beings. Can the complex organs and delicate cellular structures of a human body survive being frozen solid for decades or centuries, and then successfully revived without sustaining fatal damage? How do doctors prevent catastrophic cellular tearing caused by ice crystal formation inside human tissues? What would be the long-term impacts of such a deep, prolonged freeze on the human brain, cognitive functions, and memory retention? These represent massive, completely unsolved biological puzzles that may not possess any physical solution. The sobering reality is that human interstellar travel may simply be fundamentally impractical or impossible due to the unyielding constraints imposed by the speed of light and the terrifyingly vast distances measured in light years. Our species may be permanently confined to our own solar system for the foreseeable future, or perhaps even forever. While this does not prevent us from exploring neighbouring star systems using advanced robotic probes, the dream of human beings physically walking on planets orbiting distant suns might remain forever locked within the realm of science fiction. The reality of the light year also completely dictates and shapes our thinking regarding the possibility of making contact with intelligent alien civilizations. If advanced extraterrestrial life exists elsewhere within the vastness of the universe, a possibility that many modern scientists find highly probable given the trillions of planets scattered across space, the extreme distances measured in light years might ensure that contact remains completely impossible, even if both civilizations survive for millions of years. Let us imagine that an advanced technological alien civilization currently thrives on a planet orbiting a star positioned a relatively modest 50 light years away from Earth. Suppose they developed radio communication technology and have been broadcasting electromagnetic signals out into space for roughly a century, mirroring our own technological history. Let us ground our understanding by returning exactly to where this entire exploration began. A light year is fundamentally defined as the absolute physical distance that light covers as it journeys through the vacuum of deep space over the course of one single Earth year. When you calculate this out mathematically, it equates to approximately 9.46 trillion kilometres. This is a number so completely gigantic and out of scale with human life that it actively defies our everyday ability to picture or comprehend it intuitively. It represents a structural distance so immense that it makes our entire home planet, with all of its massive oceans, continents and crowded cities, look like an infinitesimally small, microscopic speck of dust drifting within a bottomless cosmic ocean by comparison. Yet, as thinking beings, you do not need to fully or perfectly visualize this value in an intuitive, physical way to truly appreciate and marvel at what it represents about our universe. You can easily appreciate the breathtaking, profound reality that the cosmos is vast and open, far beyond our species' biological ability to fully grasp or map out. You can lean into the awe-inspiring knowledge that the ancient light hitting our eyes tonight from those distant stars scattered across the sky has been actively travelling through the freezing void for years, for decades, for centuries, or in many cases, for entire millennia, just to finish its lonely journey right here on your retina. You can look up into the dark and truly appreciate that we live our lives tucked away in one tiny, quiet corner of an absolutely enormous, expanding cosmos. We reside on a small, fragile world, orbiting an ordinary middle-aged star that represents just one single sun inside a galaxy, which itself is merely one galaxy out of trillions scattered across the observable Webb. There is something deeply, fundamentally humbling about taking the time to understand light years and the unfathomable physical distances they represent across the void. This measurement serves as an unyielding cosmic reminder of exactly how small, fragile and geographically temporary we are when placed into the grand, eternal scheme of the universe. It highlights how incredibly brief our individual human lives truly are when they are measured against massive, sweeping cosmic timescales that span billions of years. It underscores our absolute physical isolation in deep space, showing that we are completely separated from even our absolute nearest stellar neighbours by vast deserts of nothingness. These are gaps so wide that they would require thousands of years of continuous travel to cross using any form of propulsion technology that humanity can currently engineer or build. This perspective immediately puts our daily human concerns, political arguments, and personal worries into a much grander context. It gently shows us that from a broad, detached cosmic viewpoint, the dramatic events that seem so incredibly monumental and consuming in our daily lives are actually entirely temporary, highly localized and brief. However, looking at this reality does not mean we should fall into despair, because there is also something immensely empowering and beautiful about possessing this knowledge. We must never forget that despite our physical smallness, we actually figured all of this out. Despite being physically small, fragile creatures trapped on the surface of a tiny rocky world, human beings successfully measured these vast, terrifying distances. We did not remain ignorant or blind to the nature of our environment. We used our intellect to decode the cosmos and accurately understand our true place within the universe. We designed and built sophisticated telescopes, launched robotic spacecraft into the dark, and developed complex mathematical frameworks that allow us to peer across the void and comprehend objects sitting billions of light years away from us. We are physically tiny, confined entirely to one small planet for the time being, but we are also remarkably, astonishingly capable as a species. We are conscious, thinking beings who have developed the unique ability to observe, analyse and understand the very universe that created us in the first place. We are the eyes of the cosmos, able to look up at the beautiful tapestry of the night sky and genuinely comprehend the complex physical processes we are witnessing. We can sit in our rooms and comfortably contemplate distances measured in trillions of individual kilometres, while casually mapping out vast time spans measured in billions of years. It is true that from a purely structural cosmic perspective, your physical body is entirely insignificant. Your life is a very brief, temporary flicker of awareness, lasting perhaps 80 or 90 years if you are exceptionally lucky. This footprint is a mere blink of an eye in a universe that has already existed for 13.8 billion years, and which is destined to continue expanding for trillions of years into the future. You exist for a tiny fraction of a moment on an ordinary planet orbiting an average star. Yet, you are also completely remarkable and significant in your own unique way. Every single cell in your body, and the very atoms that construct your bones, your blood, and your brain, were originally forged inside the crushing nuclear hearts of massive stars that lived and died billions of years ago. When those ancient suns ran out of fuel, their physical matter was violently scattered across the emptiness of space through spectacular supernova explosions. Over immense stretches of time, that scattered material was gravity's masterpiece, being continuously recycled and reshaped to form new generations of stars, new planetary systems, and ultimately, you. You are, in the most literal and scientific sense, made entirely of stardust. You are the direct, unbroken product of complex cosmic processes that have been operating across the universe for billions of years. Through your awareness, you represent a way for the universe to finally know itself, to deeply understand itself, and to truly appreciate its own vastness, beauty, and incredible complexity. This realization reminds us that we are not separate from the cosmos, but deeply embedded within it. We are a part of this system, bound by the exact same physical laws that govern the rotation of galaxies and the orbits of distant planets. A light year is not just an abstract measurement used to isolate us. It is a bridge of light that connects our eyes to the rest of the universe. Every single time you step outside, look up into the clear night sky, and fix your gaze on a distant star, you are actively participating in something ancient, grand and beautiful. You are looking directly across light years of space, piercing through the veil of time, and witnessing the universe in all of its unshielded glory. Thank you so much for joining me on this deep journey across the vast dimensions of space and time. If you found this long exploration valuable, engaging, or thought-provoking, leaving a quick like or subscribing to the channel would mean an incredible amount to me. Your small support helps ensure that I can keep dedicating the time required to research, write, and produce these detailed, deep examinations of our beautiful cosmos. Never forget that, even though light years represent physical distances that stretch almost entirely beyond our comprehension, they are also the very threads of light that connect us directly to the stars. Every time you look up, you are connecting with the cosmos, and this vast universe, as immense and terrifying as it is ultimately yours to explore. Good night, and may your journey through the stars be full of wonder.